Welcome back, everyone, to the second half of Make Our Planet Great Again on day one. Slight change of schedule. We were supposed to have questions, of course. Nothing was censored, but we had some technical issues, and people who were watching us live streamed, the connection broke. So we wanted them to be available for the live stream, and it's back up and running. There was another question as well, were all these presentations that we heard this morning, were they recorded? Yes, they were recorded, and they will be made available on YouTube, everything that was done this morning as well. So don't worry, that will also be available for your research labs to see as well. So I thought that since we couldn't do the questions and answers, and now that people were watching us elsewhere outside this auditorium can right now, we should do a question and answer session. The way I think we should do it is that we have a gentleman over here and a lady over here with microphones. If you have questions, stand up, say who you are, and who is the question for, so the person who you want to put that question to stands up so that they know who to give the microphone to. So these are questions directed to everyone who spoke this morning. So I know you had a question from the very beginning because you wanted to speak. So why don't you start?
Yeah, I did ask.
Someone will give you the microphone.
Hi, my name is Carol Lee. I'm from University of Montpellier and University of Wisconsin. I did have a question earlier, and I grabbed Barbara for lunch and asked a bunch of my questions, but I'll ask a corollary. I was fascinated by the fact that you were looking at atmospheric bacteria that end up floating and going elsewhere, and I work on invasive species. So I was curious about the impact of those, microbial migrations on invasions. Do you have any follow-up study to look at the impact of where those bacteria might land?
Yeah, so thank you for the question. Well, we haven't done any studies yet, but there are certainly people who look at bacterial deposition onto different ecosystems. But so far, atmospheric scientists just assume that bacteria have exactly the same properties when they're emitted and when they are deposited. And we think this is actually not the right view. And yeah, certainly it will affect the biodiversity, but we think the atmosphere does something to the bacteria, but we don't have any results yet. That will be the next steps once we put the biological processes in the atmospheric models. And then we can see how it affects the microbial population. Does this answer your question?
Who else has got a question? Next. Yeah, behind you. Tell us who you are. I think I know who you are, but tell us who you are and who's it for.
So I'm Camille Parmesan, and my question is for Henry Wu about the tropical coral reefs. And I'm not sure exactly where he is. Maybe you could stand up.
He took his snorkeling mask off.
And I was wondering, I mean, your work is obviously yet another step in level of detail from what we know about tropical coral reefs. And you're starting to see quite a bit more variation in acidification and temperature than what I've seen before. Does this give you any hope at all that tropical coral reefs might survive better than some of the earlier projections?
Thanks for the question. So there will be some winners and losers. So the corals that we use for our reef infection are more robust than the large. There's a lot of surface area for them to be eaten up by acidification versus, say, the clear corals. So we will definitely see a change in diversity in the future.
Do you have a follow-up question? Go ahead. If you have a follow-up question, go ahead. No?
So when you say the ones you've been working on are more robust, do you mean what you're seeing, the changes you're seeing, you consider to be kind of minimum for what we can expect in the future? So you're not expecting to lose the species you're working on, is that correct?
Well, we will lose these species too. Once there's a certain sweet spot in temperature that is when it gets way too hot, then we can So they are more towards the more tolerant species, and so But yeah, to answer your question, they will also disappear at some point. They're not as, yeah, they're not going to be there forever. But there are certain pockets that we've seen in coral reefs that's able to adapt, and also, but those are very specific cases around, say, volcanic vents in certain areas. I think Nuria will have actually more on that later.
Okay for you? Who's next? Who has a question? Any more? Yeah, go ahead. And Stefan, do you have anything from? No? Okay.
Thank you. I'm Alessandra Giannini. I'm at Laboratoire de Météorologie Dynamique. I actually have a question for Samuel, but I don't know if he's still around. Samuel, who was talking about snow and projections of snow. So maybe I won't ask.
But he's not here?
Yeah,
There he is.
he's there? Ah, okay. Hello, Samuel.
Do you want to
Yeah.
ask the question again? We didn't hear it very well.
Yeah, no, I didn't ask the question yet. The question is whether you actually, you talked a lot about projections, but in climate services, do you also use seasonal predictions in these decisions that you were discussing about what to do for the next winter?
Yeah, it's a good question. So what I talked about this morning is about long-term projections and how to adapt the ski tourism infrastructure in the longer term and the future of those territories. We have actually worked on a project where we used the same kind of models which account for snow management, including snow production, fed by weather forecasting and seasonal forecast, because there is some memory in a snowpack in a way. Like if you start from the 1st of December with 1 meter of snow, you know that it's not going to melt immediately. So if you can, we built a demonstrator, and we actually built another service, which is not called ClimSnow as this morning, but ProSnow. That was the name of the project. You can look it up on Google if you like, or any other browser. And in which we basically plug the same kind of tool using weather forecast and seasonal forecast so that the ski resorts managers can adapt real-time choices in terms of snow management using weather forecast at a number of timescales to optimize the management. Because in terms of resources, what you want to avoid is that you produce snow, usually it's in November, December, that most of the snow is produced, and then there is a warm spell, and all the snow melts away. So you wasted a lot of resources, water, energy, manpower, and you don't have snow anymore on the ground. So there are ways by which we think we can help this industry to optimize how to cope optimize the use of the resources. And this allows me to connect to another item in terms of climate change adaptation, is to remind ourselves that climate change adaptation is not only about infrastructural changes, but it's also through early warnings. So if you can anticipate extreme events, or if you can anticipate weather conditions at scales of hours to days to weeks, to some extent you can also reduce some of the risks that are maximized by climate change. So I think we should never disconnect the weather forecasting with the climate change context, because they're mutually interconnected, and through better forecasts at short time scales, we can also better adapt to the worst consequences of climate change. And I'm not only talking about ski resorts here, but also extreme weather events, high precipitation episodes, etc.
Another question from anyone? In the back there. Tell us who you are and who it's for.
Hi, it's Jim Clark from, am I turned on? Jim Clark from University of Grenoble and INRAE and Duke University. I also had a question for Samuel. You showed this increasing water use to produce snow. And first of all, I wondered if that's going to be an issue for water availability. But I also wasn't clear how you came up with that, because it seems like if you've got less ski resorts that are cold enough to produce snow in the future, that the water use would actually go down. So I wondered if you could also explain that.
Yeah, those are excellent. Yeah, those are excellent points. Thank you. So the models that we developed produces snow according to different rules which are implemented in the ski resorts. So we have some kind of a decision tree in the model that if the weather conditions are good enough, like if it's sufficiently cold and the wind is sufficiently low and the humidity is sufficiently low, then with a given target production, the model will try to produce some snow. And so we record how much water is used, and that's how we come up with quantifying the water demand for production. We don't pair that yet with whether this resource is available. We compute the water demand, and then this can be used by further specialists or further studies combining that with whether this resource is available. So, but that's then a second step. But we compute the demand. And whether this is going to be a problem, it depends, as usual. It depends on the location, depends on the hydrogeology of the locations, and whether there are ways to store the water or whether the storage is an issue itself. So there are very different situations in the ski resorts with that, and we are, of course, well aware of the situation currently in Haute-Savoie, where there is some kind of a number of events of protests about the installation of a new pond, a new lake for providing water for snowmaking. So those are clearly very, very, very critical choices that are made at the very local scale. And I think to some extent we're providing the evidence or providing the element for those locally informed choices to be made. And yeah, and to July's point is if some ski resorts close, at some point, yes, this water will not be used anymore. In the simulation and the result I showed this morning, it's for a fixed geometry of simulation. That is, if we take all of the ski resorts of today and we keep all of them until the end of the century. And then, and of course, this includes ski resorts for which there is still some water demand, because there is still some attempts by the model to produce the snow, even though it melts quite quick. And so there is no guarantee that the water used contributes to to snow conditions which are favorable for skiing. So this is clearly an estimate of water demand for business as usual snow management as of today with today's technology, and this is a baseline for discussion, not more than those are scenarios, right? So it's not what the future will be like. Those are different pathways that we can use to explore the possibilities.
Thank you. Question over here. Put the microphone right next to your mouth. Tell us who you are.
Can you also address questions?
Yes.
Thank you. So I'm Philip Schulz from CNRS IPVF, and my question is to Fred Bouchard about the release of CO2. So you mentioned that with the breaking of the permafrost, you would release CO2 in the atmosphere. I had on my mind that also other atmospheric gases are stored or released, like methane. Now my question is, am I widely off here? And then second, how do you assess on how much gases actually escape from the permafrost soil?
Who's answering?
He's online. He's online, yeah.
That's going to be tricky, I think.
Okay. All right.
I suggest you send them an email.
All right, we'll do that.
We had a discussion about this, and we think it's a bit difficult to do. Okay. Anybody else? Go ahead.
My question was for Jerome Chauve, and I was you brought this up in your question about the plantation forest versus natural forest, and I know some of the literature on this, and what puzzles me is why, when you talk to forestry people, they still seem to think plantation forest are a wonderful carbon sink. And in COP26, I think they were still talking about plantation forestry as being, part of your lowering your carbon emissions, getting your carbon balanced. So I'm wondering if there's something scientists are not doing to get the message across? And if you've worked with forestry people, sort of forest management people, and found them to be, are we using the wrong words, or is it actually that they're resistant to the idea that plantation forest might really be the wrong thing to be doing?
Thanks, Camille. That's a great question. I don't think there is a good answer and a good solution. Plantations are not bad and natural growth good. It depends really on the perspective from an economic standpoint and a local development standpoint as well. In all Europe, we're witnessing plantations mostly. And there's good reason for this, because it's an economic resource for most territories. And this is exactly the model applied in many countries in the tropics as well. So it would be really difficult on the side of European countries or northern countries to impose different regulations for the countries of the global south. That being said, from a purely carbon sequestration perspective, it's clear that plantations are not the optimal solution. The answer is not white or black. It's just a question of perspective, or what do we want to achieve with one solution versus another solution.
But they're being used to create, but that's what I meant, is countries are using plantation forest to balance their carbon budget. And for the information you were presenting, and from papers I've read as well, this is a very false, superficial way to lower your carbon, to get your carbon budget balanced. And so that's what I meant, is
you're right.
If this is not the right thing to do in terms of creating the best carbon sink, why is it persisting so much?
So you're right, there is a potential loophole here in that you could sell plantation as really effective carbon sinks, whereas they are not really. And the reason why it's persisting is because locally plantations bring revenues, and also the plantations become part of the global commodities, so they enter the same global markets and a capitalistic system. So I guess there are good reasons why the misinformation is being carried along.
Thank you.
Any more questions? Great. We will have another question session, of course, because we have a lot more speakers to come. And also, if you are watching us online, and I can see that some of you are, you can send us questions. You can send us, but we've got Stefan who will be taking any questions. So if you have questions coming up throughout the afternoon, we can get those across to the speakers as well. So why don't we move on then to the next session? And once again, I welcome Gayon back up. With her, she's the chair, and it's feedbacks on climate change. So all her team, why don't you come up? Gayon, why don't you sit there? And you'll sit over there. And Guy, why don't you introduce your team, okay? The panel, who's here and who's remote.
Hi everyone again, and thank you for joining to this session, whether virtual or in person. I would like first of all to take the opportunity and to acknowledge to the MOBGA conference organizers, and as well our MOBGA project organizers and our grant providers, supporters that allow us to make our research possible. And of course, I would like to thank also all the laureates for their time and contribution. So the next session is about feedbacks on climate change. We are going to have 5 talks. One of them will be online, and the other talks are very diverse, ranging from southern ocean clouds, imaging of zooplankton, and ocean alkalinity, and so on. And please, Anna, if you are ready, stage is yours.
Thank you, and hold on a sec. Good afternoon, everybody. Here we go. Can I have my slides? There we are. So we're going to start off by going into a very remote region of the planet, and that's the Southern Ocean, and spend some time with trying to understand Southern Ocean clouds. And in particular, we're going to be looking at marine stratocumulus, which is the single most effective and widely spread cloud type in cooling our planet. These clouds form very close to the surface, so they have a very negligible long wave effect, so that's the terrestrial radiation escaping back into space, while at the same time they reflect between 20 and 40% of all incident solar radiation. And these vast cloud sheets really spread over hundreds of kilometers and cover the Southern Ocean in particular between 20 and 25% all year around. And their primary function in the climate system is to reflect sunlight and to provide shade and thus cool the surface. Now in the Southern Ocean it gets very cold, so many of these clouds form not just in temperatures above freezing, but in a supercooled regime. So some of these clouds really form under conditions of minus 25 degrees Celsius, even though they're so close to the surface. And that means that they don't only consist of cloud water, but also of cloud ice. Now, if you study these clouds, then you know that the thermodynamics tells us that as soon as you're super cool and there's ice, the ice state is always energetically favorable. So all the water, as soon as both of these phases coexist, should disappear. So the ice crystals are, in theory, freezing enormous holes into our parasol and rendering its reflective capabilities far less efficient. But the dynamics and the microphysics of these clouds is such that the water is constantly regenerated, so that these clouds still persist for hours and days in these regions and are still cooling the Southern Ocean locally, but as well as having a cooling effect globally. And here I show you a spread of what we call the low cloud feedback between different model runs, and I only want you to focus on the orange dots on the very right-hand side. They show you the shortwave cloud feedback, and it's quantified as additional watts per meter squared in warming per Kelvin degree of surface temperature change driven by CO2 forcing. For context, if you're not really familiar with watts per meter squared of warming, the current CO2 forcing is about 4 watts per meter squared. And you see in the orange circle the newest generation model climate runs and quantifying what the shortwave low cloud feedback is. And as you can see here, if you compare it to the axis on the right-hand side, there's really a huge spread amongst these models. They agree that our parasol is going to be weaker in future climate, but how weaker is really highly uncertain. And that uncertainty predominantly sits in Southern Ocean stratocumulus clouds. So this is why this is such an active field of research, because it's still introducing a tremendous amount of uncertainty in climate predictions. So in this MOPGA project, we use a two-tiered approach using both active remote sensing as well as numerical models to understand these type of clouds. The active remote sensing observations have strong positives as well as drawbacks associated with that, as well as the numerical simulations. It's kind of always the case, isn't it? So while we have decades of continuous records, and the active remote sensing allows us to probe at least the cloud top regions of these stratocumulus, we get vertical resolved information on cloud phase and cloud locality, cloud top temperature, and all these types of things. But as Matthias was saying earlier in the previous session, we lose spatial context and we can't really track the evolution of these type of clouds. Now all of this is available in a model, but many of these mixed phase cloud processes that I was hinting at earlier are either not yet well understood, or even when they are understood, are still poorly represented in most climate models or even mesoscale models, and yet even LES models, I have to say. So this is still a very actively ongoing research area, going far beyond MOPGA. So the results that we found in our studies so far within this framework was that we addressed this question of how cloud phase and how cloud patterns, so the different weaving patterns of our parasol, are interlinked. People have hypothesized that phase and pattern are interlinked and have a combined impact on albedo, and we could not verify this in long long-term climate records using active remote sensing. And then on the numerical modeling side, we've been working with a relatively new climate model, ICON, which has been co-developed by the German Weather Service and the Max Planck Institute for Meteorology. And ICON, like many other GCMs, is unfortunately doing a relatively poor job in southern ocean stratocumuli. They produce too much ice and are not reflective enough. And we're working on improving that within these simulations at the moment. So the take-home message, the really basics of this, is that if you want to understand what's happening over thousands of kilometers, over decades and hundreds of years, for these types of regions and clouds, you really have to zoom in to the microscale and understand what's happening between these crystals and these droplets on a timescale from seconds to minutes. There's unfortunately no way around it, and yeah, that's where we are.
Thank you. The next speaker is Ashley Balantin, and we have the recording. Now we can have the talk.
Hello, my name is Ashley Valentine, and I'm a Make Our Planet Great Again Fellow. And I would love to use this opportunity to share with you some of the results from our project investigating hotspots of carbon climate sensitivity, focusing on regions and processes. And what better way to make our planet great again than investigating in great young scientists? So I'd like to share results with you from my colleagues Julia Green, Minjun Kwan, and Kailiang Yu. So if we look at the global carbon cycle, what's immediately apparent is that roughly half of the carbon emitted as CO2 into the atmosphere, either through fossil fuel emissions or land use emissions, does not remain in the atmosphere, but a quarter of that carbon is taken up by ocean sinks, and another quarter is taken up by land carbon sinks. But what is also immediately apparent is that most of the uncertainty in the global carbon cycle is associated with this net land uptake, where 2 petagrams of carbon are taken up every year, plus or minus 2 petagrams of carbon. And a petagram represents 10 to the 15th grams of carbon. So a massive amount of carbon taken up by terrestrial ecosystems, but a massive amount of uncertainty associated with those land carbon sinks. So to get at this uncertainty and what might be causing it, Julia Green focused on the Amazon. And in particular, she was interested in how we might better use satellite measurements of land surface temperature to determine which regions are light or water limited. And what she discovered was 58% of the tropics are water stressed due to radiation, and these tend to be the high biomass regions here in green. 30% of the tropics are water stressed due to soil water supply, and these tend to be the low species richness regions in blue, and 22% of the tropics are water stressed due to atmospheric water demand, and these are the red regions of tropical South America here. And when these instances of high atmospheric water demand coincide with low water supply, this vegetation water stress can lead to an 80% reduction in carbon uptake. So a huge amount of carbon not being taken up by the Amazon due to vegetation water stress. Another sensitive region in the global carbon cycle is the high Arctic, where temperatures are increasing at twice the rate of global temperatures. And of particular concern are peatlands at high latitude that are underlain by permafrost and the fate of the carbon in these peatlands. So Minjun Kwan, for her PhD work, manipulated a peatland in Chersky, Siberia, and drained this peatland to look at the fate of that carbon. And for her postdoc, she has been looking at a comparison across sites. And what she's discovered is that across the Arctic, as these peatlands are drained, they release more carbon to the atmosphere, but more carbon as CO2 and less carbon as methane. So a net release of carbon to the atmosphere, but less carbon released as methane upon draining of these these peatlands at high latitude. Lastly, Kai-Liang Yu was interested in using forest inventory data from the world's forests to estimate carbon residence time. So how much time your average carbon molecule spends in a forest. And what he found was that even though tropical forests have the highest biomass, they often have the highest biomass loss due to mortality. And this led to the longest carbon residence time actually being observed in temperate and boreal forests, in contrast to tropical forests, which may slightly alter our conservation efforts. If we're interested in biodiversity, we might focus on tropical forests, but if we're interested in storage of long-term carbon, we might focus more on temperate and boreal forests. So lastly, in conclusion, increased water stress can lead to diminished CO2 uptake by tropical forests, especially if biodiversity is lost. So forests with lower diversity of traits tend to become more water stress and take up less carbon. A warmer and drier Arctic could lead to increased CO2 fluxes to the atmosphere, but a slight decrease in methane fluxes. And we discovered that carbon spends more time in temperate and boreal forests, which may alter our conservation efforts if we're interested in carbon storage long-term versus biodiversity. Thank you very much for this opportunity to share my results, and I look forward to any questions you might have.
Okay, next speaker is Thomas Lavo. The title is Atmospheric Monitoring of the City Pledges.
Hi, everyone. Pleasure to be here and present some of the results. I want to thank my partners, my collaborators, Philippe Sier and Valérie Gros, both at LSE. I mean, this effort is not only mine, there is a whole lab and a lot of people behind it. I wanted to talk about cities and why cities. We just finished the COP26 and all nations were involved. Well, what we don't talk much about is the subnational level. There are a lot of actors at subnational levels that really want to play their role in the climate change fight. And cities especially, because cities represent up to 70% of the fossil fuel emissions around the world. Directly, it's about 50%, but they consume a lot. Wealth are there. They actually buy, import, export a lot. So cities are key areas in the world to actually track and fight climate change. But when you look at what happens over the US and you take about 50 cities, take their carbon accounting, so that's their own calculation of how much carbon they release, and you evaluate it, you realize that there is an enormous bias in their data set. It's about a 30% on average underestimation of their actual emissions. Why that? Because a lot of the information is not trackable. You cannot track industrial data. It's under privacy. They don't have access to domestic fuel. They don't have access to a lot of data that actually are not even collected at this stage. So what can we do to help them? Well, we can do exactly like we've done when air quality became a health concern. You can track emissions from the atmosphere. So here's an example of how you can do that simply by deploying sensors around the city, running an atmospheric model, and making the optimization between what you're supposed to see and what you have actually observed in the atmosphere. We did that with LSE, deploying sensors around the Paris-Île-de-France area. You see Paris in the middle. You have an idea of the density of this area. It's about 12 million people living in that small fraction of the French territory. You see the wind coming from the southwest, where we're on the mid-latitude, so it's always the wind you're going to meet at that latitude, more or less. We see what's coming in, and we see what's coming out. The difference between these two is the emissions released from Paris, and we track it. We measure it, and what happened last year was an unfortunate event, but actually for us, an incredible experiment. Paris shut down, which never happened before. People just stayed home, stopped using their cars, stopped going out. And this is what we have measured directly, day by day, week by week, as you can see in the 2020. 2 confinements happened. One, the first one, very strict, schools were closed, nothing was happening. You can see the impact during that first yellow period. The second one was actually a little less strict. Schools were open. You can see the impact, 42 to 50% decrease in the emissions for the first confinement and 20% about for the second. Well, Nice, the system was able to track that. It's in line with the estimates we got from the Air Quality Agency of Paris. But, scary part of that, you shut down Paris, you still have 60% of the emissions, which I think for us was the strongest message of all. The structural emissions, the ones you can't touch, were still there and very hard to remove from that system in place. Okay, but here is the reality of the world. That's a nice little project, but this cost a lot of money just to make one city. And we have a lot of cities. You can see on this map just a sample of what you're going to find. It's only 2% of the surface of the globe, but my God, if we had to deploy sensors all around there, it would be a disaster. It could take 10 years and billions of dollars. So how are we going to solve that at the next scale? Well, satellites. They look great, people love launching satellites, and they can bring you very useful data. I want to highlight two missions, one from the US that is actually flying right now on the International Space Station called OCO3, and the second one that is in development to be launched in 2025, the CO2M mission by the European Space Agency. What do you see from space? And this is an example of a Washington, DC and Baltimore. Well, you can see now this mapping of the area. The satellite will very rapidly scan over, collect several bands of CO2, and we try to model that. Well, can you see DC in that map? It's incredible, 15 million people, and so hard to detect, because we have released tons and tons of CO2 for 150 years. So the emissions of DC are a little tiny fraction on what you're going to find in the atmosphere, meaning we need this really high-performing satellite to even capture plumes from megacities. So we're working on it, and we might not be there yet, but it's coming. So my final message is very clear. A lot of cities have pledged. They have pledged to reduce their emissions. They invest millions of dollars. But the truth is, they don't know where they are right now, and they are not even sure where they are going with their investments. So we need to help. And one way is to bring more data to that game, bring science-based information so that they can take the political decision based on actual numbers and not on speculations on their carbon emissions. Thanks to you all.
Thank you. Next speaker is Rainer Kiko. He will talk about imaging of zooplankton. Please.
Yeah, thank you very much for the chance to present. Just waiting for my slides. So my name is Rainer Kiko. I'm from the Laboratoire d'Oceanographie de Villefranche, and I will present about imaging zooplankton and particles in the ocean of change. And I want to especially thank Marc Picheral, who actually over the last 20 years or so developed the instrument that we are now using to do this kind of things. So to start the talk, I want to show this slide that brings us also back to the last talk, which is the amount of CO2 in the atmosphere. And I think that this curve actually brings us all together here, because the increasing CO2 actually leads to global warming, and that is something that we have to stop. What we also know, and we heard about it already today, is that we have these emissions. 7.2 gigatons of carbon per year are produced, and we know that the atmospheric increase is smaller, and that's due to the fact that the land takes up some of this increase, but also the ocean takes up some of this increase, and the ocean is actually, according to this source, the most important sink for the increased emissions. So, what happens to the CO2 in the ocean? And this is what I want to talk about today. So this actually, up here on the left side, so you see the small area of the CO2 going in, and then all the complex things happening in the ocean. And this shows a scheme of the oceanic biological carbon cycle, and you can see that we have many players there, and something like aggregates, zooplankton, things like that. And actually what we do in Villefranche, as I said, Marc Picheral developed this instrument that we are using now for several years. We image particles and plankton in the ocean. So this camera system that you can see here, there's a camera in this the metal cylinder in the top. The camera is looking downwards, and you have an illuminated light field at the bottom. And we image zooplankton and particles in the water column down to 6,000 meter depths. And so we've done that over the years to actually learn whether the ocean can keep up, and to, for example, study aggregate formation and sinking of particles in the ocean. And the carbon content and sinking speed of particles actually in the ocean, it depends on size. And so based on size measurements of particles, we can actually get to an estimate of carbon flux in the ocean. As I said, we, over the years, used the Underwater Vision Profiler to obtain data all over the place. And this is a map that I could actually compile also due to the MOPCA funding, where we now have compiled 9,000 profiles of carbon flux, so to say, with the Underwater Vision Profiler 5. And you can see that this is really an international effort to get this data, and France, because the instrument was developed in Villefranche, is of course a major player, and I worked in Germany before also to gather much of this data. And what we do now is we take the particle data, we join it with temperature, chlorophyll A, and particle flux estimates from other instruments, for example. We use artificial intelligence to actually get to interpolated data. And this now is a map of carbon flux out of the sunlit ocean, so the euphotic zone where actually the carbon is fixed. And we can integrate that, and we can learn that we have 6.7 gigatons of carbon taken up by the ocean per year. Which for me is also to some extent surprising, because the ocean only takes up 2.2 gigatons of carbon at the ocean surface. So there's a discrepancy that we need to somehow resolve. We also know that the deep ocean actually receives only 0.7 gigatons carbon per year. So something happens in between these two borders, the border of the zeophotic zone and the border of the deep sea, and that's some things we have to understand better, because somehow the numbers don't match, and we don't understand the carbon cycle in the ocean to the extent that we would need yet. So we really don't know if the ocean keeps up, and we need higher spatial and temporal coverage. And this is something that we also, due to MOPCA funding, but also to other funding, can do now. Also, again, due to Mark Buscheral's engagements in developing the systems further. So we now have the Underwater Vision Profiler 6, which is a much smaller unit, and you can maybe see it on this Argo float on the left side. It's a very tiny instrument now, and we can deploy it on these floats, and we can throw them in the ocean, and we can get real-time profiles of particle distribution in the ocean. And so we now have 6 of these floats deployed all over the place, and yeah, this is really amazing to get this in situ real-time data on carbon flux in the ocean, and yeah, we need to deploy more of these, I think. And that's it. I also wanted to give you a nice view of Villefranche. Thank you.
Thank you. And the last speaker for this subsession is Helmut Thomas, and he will talk about ocean alkalinity.
Thank you very much, Kaini. Good afternoon, everybody. Yeah, as Kajan said, I'm Helmut Thomas from the Helmholtz-Zentrum Hereon near Hamburg. And I will talk about the ocean's alkalinity, which serve as a connector between metabolic and geological timescales and processes. And I was impolite enough not to mention the whole group who actually did the work. Johannes Petsch is here, but there's many more involved, and I show some of the results of the colleagues. Next slide, please. Oh, I can click. This one? Yeah. So we have talked about many of these aspects in the morning and the afternoon. Also, Rainer showed a different slide of the global carbon cycle, so I picked a very simple one on the left-hand side. In the end, the main reason is to differentiate between short-acting or fast-responding reservoirs and slower ones. So on the left-hand side, you see the biology on land, but also in ocean. And as I said, Rainer showed a very nice slide or picture of the ocean biology, which are on seasonal or weekly or multi-annual timescales. And then you have the subduction, and our problem maker is basically what is called human activity. So this is a little red arrow connecting the fossil fuel reservoir with the atmospheric reservoir. And then on the other side, which I touch upon later, is the geological or weathering activity, which controls the carbon reservoirs on a very long time scale. And in the middle, basically, there are the atmospheric CO2 reservoir and also the dissolved water columns CO2, which is called DIC. And this is, in the end, the property we want to talk about. And the regulation of this reservoir in the ocean is done by two factors. One has been nicely explained this morning by Stefan Rahmstorff, so this is ocean circulation. And the other one is a biogeochemical control, this is alkalinity. And this, in the end, is a product of rock weathering, which we also have talked about in the morning quite a bit. And this does show you the right-hand side panel. So we have basically the rocks and the soils weathering and releasing bicarbonate and entering the ocean as alkalinity. And this is, in the end, the cycle which is shown there is a silicate weathering thermostat, and it regulates the temperature on Earth on very slow time scales. And the question of our investigations is whether there's actually short-term variability or vulnerability of this very slow long-term cycle. And this points to the fact that we can identify two sources of alkalinity. One is the erosion one, which is shown there, but there's a second one, which is a metabolic produced alkalinity, and this is exactly what is missing on Rainer's slide, namely the shallow sediments. And this is also hardly visible on my own slide because these are the sediments and port areas basically next to the coastline where anaerobic processes can happen, which actually produces anaerobic metabolic alkalinity. So I won't talk much about the weathering part. Here you can see some oceanographic fieldwork in the Alps, but also in the Bayerischen Wald, in Schwarzwald in northern Norway, where we actually took samples to investigate the processes leading to the carbonate release as a function of soil and rock composition. This is a result which we are in the middle of evaluating the data, and so I wouldn't talk about this too much. Instead, I would like to focus rather on the metabolic part, which is a study from the German Elbe River and the Hamburg port area. So we took one of our small ships and basically sampled the Elbe from Hamburg, which you can see on the left, top left panel, and then downstream into the North Sea. And we measured the two carbon cycle properties, which I just mentioned, alkalinity and DIC. And this is a top center panel, which is a little bit too scientific maybe. But the interesting part here is that there's in the port area, which is actually shown at the second and fourth point on the right-hand scale. So it's about kilometer 620. There's a massive increase. And this is exactly basically the area where the sediments of the port are very active bioreactors and release CO2 from respiration of particulate organic matter and alkalinity in massive quantities, which enter then the coastal ocean and impact the CO2 fluxes in the coastal ocean. And if you look at the mass balance on the top right side, you can see that in the end downstream river is not much happening anymore, but the really active region is the port area. And if you make the inventory, then you can see that in the end about 15% of the CO2 and alkalinity released to the North Sea are basically of this metabolic source. And if you want, you can make the balance for the Elbe River. This would leave you with 85% of weathering alkalinity or from soil erosion, basically upstream the Elbe River. And the main question which we now pursue is, since the humans are very good in regulating this metabolic activity by nutrient inputs, we want to see how this relationship changes and whether there's eventually, due to reduction of eutrophication or increase of eutrophication, an increase of this metabolic production or decrease of metabolic production. And the second question is, which we want to address, whether also climate change and anthropogenic change has an impact on the weathering-driven alkalinity release to the ocean, which then would overall allow us to constitute a positive or negative feedback to climate anthropogenic change of the open carbon reservoirs, ocean carbon reservoirs. Thank you.
Thank you, everyone. And if you have questions, you can prepare them for Q&A part.
Okay, thanks very much. So we'll do questions later. Yeah. So thanks very much to all of you for participating. We'll do more question and answers about 40 minutes from now. We're getting some questions online as well, so we'll have those for you all as well. In the meantime, we're moving on to the next theme. And for that, it was supposed to be Matthias, but he's remote, so I'm kind of going to take over. The angle is new challenges for Earth system modeling and forecasting. So, can Ridouan Liggenstadt join me, as well as Julien Bouchard? Just put yourselves in chairs there. Ridwan, I think the calibration of coupled climate models with multiple intrinsic timescales. From Princeton, now working with CA, Laboratoire de Sciences et Climat de l'Environnement. So, go ahead, it's all yours.
Yeah, thanks. Hi, everyone.
And you can use that.
Yeah, sure. Okay. Hi, everyone. My name is Ridwan Gensat, and I'm actually a representative of the Hermes MOBGA project led by Venkatamani Balaji. And today we'd like to talk to you about an application of artificial intelligence to climate modeling. But before that, I would like to talk about a historical event that happened this year. It's related to the Nobel 2021 Prize in Physics. Did you know that half of the prize went to 2 climate modelers, which was really, really exciting for me and my colleagues, and I know a lot of people here. So Manabi and Mahassaman are climate modelers, and they worked with their teams, of course, on developing new climate models and on doing climate projections. We do have here 2 examples that date back to the 60s. For example, Manabe, he showed that in his climate models, when he added a lot of greenhouse gases, he found that temperature increases, right? So this was a 1D model, a very simplistic model. Then he went with his colleagues again and tried with a 3D model, and he found the same conclusions. So climate models help to reliably predicting global warming. So those were simplistic models, but now the story did change. We do have high resolution model. You won't believe me maybe if I tell you this is not a satellite image. This is coming from a model simulation. So as you see, it's a high resolution. We can have now more accurate physical modeling. And this was done thanks to a lot of improvement in computing capacity, improvement in storage capacity, etc. But there is a catch. Climate models are very expensive, and some processes are still hard to represent. For example, eddies in the ocean, clouds in the atmosphere. If you see, for example, when we work on a grid, sometimes the grid is larger than the clouds, for example, in the atmosphere, so we cannot represent them. So for that, we use a solution called parametrization. The idea here, we add some equations that have some parameters, and we try to compensate the effect of these unresolved processes. So as I told you, the parameterizations are based on some parameters that we need to choose. That's what the MOBGA Hermes project is about, is using artificial intelligence to tune climate models. So what we are doing here is trying actually to not do like what people are doing now, climate modelers now, because now they are really tuning by hand. Most of climate modeling groups are tuning by hand. For example, if you had parameter alpha, which is comprised between 0 and 10, they just like choose the value 5, run the simulation model, and see if it matches the observations. If it doesn't work, they go back, they choose parameter 3, alpha equal to 3, run it again, and this is very, very expensive. For example, for the model, for the French IPSL model, it took 5 years to find an acceptable tuning. Okay, so what we are doing here is trying to use AI, artificial intelligence-based emulators, to replace the expensive climate model, all right? We use this just to find good tunings, okay? So we do this just to find an acceptable or a group of acceptable tunings, and then we can run the expensive, the real climate model with these parameters, with the good parameters. So I did try the method on a simplistic model called Lorentz 96. Lorentz 96 has 2 coupled variables, a slow one, x, and a fast one, y. Okay, you can see that as an analogy with the coupled ocean atmosphere models, where x, the slow variable, is the ocean, and the atmosphere is the fast variable. And the technique is called history matching, and we applied it successfully on this model. So of course, the next step is to apply it on realistic climate models. So if you are very interested by applications of artificial intelligence to ocean, climate, atmosphere, please do not hesitate to check our latest review paper on the subject. And yeah, that's all for me. Let's make our planet great again.
Thank you. Thanks very much. Unfortunately, Ushida Takaya was supposed to join us here, but he was feeling unwell. But we showed no mercy and made him record his presentation anyway. So here is his presentation from Ushida.
My name is Takaya Uchida, and today I'll be talking about harnessing realistic ensemble ocean simulations as a new tool in examining the Gulf Stream. I've listed my collaborators below and along with their photographs. So what you see here is a simulation, numerical simulation of the North Atlantic Ocean. And as some of you may know, one of the characteristic features of the North Atlantic Ocean is the Gulf Stream, as you can see as the energetic current shooting off from the east coast of the US. And if you trace the origins of the Gulf Stream, you can probably see that it's coming from the south, hugging along the east coast of the US and Gulf of Mexico. But basically, it's coming from the tropics, and meaning carrying warm waters from the tropics northwards to the Arctic. So the Gulf Stream has a huge signature on the global climate by transporting heat from the tropics to the Arctic. And the Western Europe winters benefit a lot from this heat that comes from the tropics to the north. So just to recap, the Gulf Stream is an energetic current that transports heat from the tropics to the Arctic, impacting global climate. And what I show on the bottom is a schematic of where the Gulf Stream is warm. So there's a lot of evaporation that goes on above the Gulf Stream, which causes low pressure systems, namely storms. And these storms tend to propagate eastward, affecting the weather of Western Europe. So this is just another way that the Gulf Stream impacts Western European weather and climate. So modeling and understanding the Gulf Stream properly has implications for understanding climate. So we want to, so a lot of emphasis in the field of physical oceanography is to trying to understand the Gulf Stream system itself. But in order to do that, we first need to be able to extract the Gulf Stream signals. And what I'm showing you here is a figure from Alui et al. 2019. And they use a spatial filter to decompose the large-scale flow and the small-scale flow. If you add these together, the right two panels, you get the total actual flow field. But the point here is by using a spatial filter, the large-scale flow captures the Gulf Stream, and the small-scale flow captures the flow around the Gulf Stream. And using this mechanism, Louis showed that on the bottom left panel that the small scale flow tends to energize the large scale flow, aka the Gulf Stream. Here, instead, using a spatial filter, we have proposed an ensemble framework where on the left I show a snapshot of snapshot on January 3rd, 1967 from our 48 ensemble members. And the way you can consider these ensemble members is that, taking a step back, if you know the term butterfly effect, it's an effect where, if a butterfly flaps somewhere, it rains somewhere else. And what that effectively means that when the system is chaotic, a very small perturbation, such as a butterfly flapping its wings, can lead to a large change in the system, such as a weather change in another location. The ocean itself is also a chaotic system. So what we do is that we perturb the initial condition 48 different ways, and then let the system run based on those 48 different perturbed initial conditions. And so you can consider this as the oceans in 48 different parallel worlds. But anyway, so you can get a realization of January 3rd, 1967 in a 48 different state. And by doing this, what we get out of it is that when we take the average over these ensemble means, we can capture the large-scale Gulf Stream state, as I show on the right, as you see as the thick yellow line shooting off from the east coast of the US. So what this allows us is that it captures much more spatial detail than the spatial filter, as I showed you here. And without going into too much scientific detail, I'm just going to say that this allows for a better understanding of the Gulf Stream and impact on the climate because it captures more detail. And I would like to finish by showing the publications that came out of the mock project, and I would like to finish. Thank you very much.
We're going to stay remote now and talk to Philippe Lucas-Pitcher with climate change impacts at the kilometer scale over Europe. Philippe, can you hear us?
Today I'm going to talk about the new generation of climate model, so-called convection permitting regional climate model, that emerged about 10 years ago. This new type of climate model is at the heart of my project, which consists to take advantage of this new generation of climate model, the convection permitting models, to quantify climate change impacts. For those who are less familiar with climate models, such models consist of numerical programs that are based on physics equations. In order to perform a climate simulation, we need to discretize the atmosphere in 3D rectangles as shown here. In theory, the smaller the rectangles, the better it is. It is like a TV. The more pixels you have, the best image quality you can get. However, there is a limit in the reduction of the rectangle size that is linked to the computational power of supercomputers on which these models are run. In the end, a climate model is a virtual laboratory of the Earth system that we can use to test some hypotheses or to perform climate change projections that depend on forcings such as greenhouse gas scenarios. So we have global climate models that are run on the full globe that are limited to around 150 kilometer resolution according to today's supercomputer power. Then we have regional climate models in which the available computer power is used to simulate only a region of the globe. These models are driven at their boundaries by global climate models and can reach about 10 to 50 kilometer resolutions. Finally, we have convection permitting regional climate models that can go at even higher resolution, about 2 kilometers, on a smaller domain that is driven by a regional climate model. At 2 kilometers, the deep atmospheric convection, which is the main mechanism that builds storm, is explicitly simulated. This is a strong advantage since we don't need to use parameterization or approximation to represent such processes. So to recall, the main objective of my project is to take advantage of the state-of-the-art convection permitting regional climate models to compute local scale climate change impacts that were difficult to simulate or to compute until recently. So the project is about halfway now. The climate simulation have been done, and we are now focusing on the evaluation of these simulations using observations. The main focus is the added value, or in other words, on the improvements that we can get using higher resolutions. I am supervising 3 PhD students. First, Joanna is interested on the impacts of climate change on the urban heat island. With darker buildings, heat capturing materials, and heat releases, cities are usually warmer than the countryside. This is reflected in our climate simulation, but at 12 kilometers, the resolution is not high enough to simulate this feature correctly. I'm showing this feature here with the summer mean 2-meter minimum temperature over the Paris region. However, at 2 kilometers, the simulated urban heat island is getting closer to that observed. I am also supervising Niels Poncet, who is interested on the impacts of climate change on flash floods. To give you a better idea of the outputs of a climate model and on the advantages of convection permitting models, here I'm showing an animation for the month of January 2000, in which we can see the precipitation in blue and yellow and the snow in gray and white. At higher resolution, precipitation extremes are stronger and improved. The frequency of precipitation is also more realistic, and the distribution of snow is also better spatially distributed. These drivers are important to improve the simulation of floods with hydrological models. Finally, Virginia, that has started a few months ago, is interested on the impacts of climate change on the climate of Corsica Island. So once the evaluation will be done, we will focus on the climate change and we will try to quantify local climate change impacts that will be useful to determine appropriate adaptation strategies. If you would like to know more about this project and about convection permitting models, I invite you to have a look at this paper that I wrote with collaborators and which was recently published in the journal Wiley Interdisciplinary Reviews Climate Change. Thank you for your attention.
Now, the next person, Julian, was actually sitting next to me on the plane yesterday, and he was a surfer in Hawaii, and he's managed to turn that into a Make Our Planet Great Again scientist. So there's hope for all of us. Over to you.
All right, guys, so good to see you all. It's been a while. Since last time in Paris, I actually expanded my research program on tropical cyclone. Yep, to not only study their processes and mechanisms, but now also their dramatic coastal impacts. So today I'll be talking about coastal vulnerability. So what is it exactly? It's a bit of a catch-all terms. It's been defined as the susceptibility of a coastal area to be affected by either flooding, as you can see here on this picture in New Zealand, or erosion processes, as you can see on this beach here in Hawaii. I actually took that picture, Chris, that's where I used to live. And the waves were big that day. So why do we care? Because actually 600 million people live at less than 10 meters above sea level, and that without any mitigation, that could lead to the displacement of up to 200 million people by the end of the century. For example, it's already happening here in the Maldives, as you can see in this picture. So now what causes these extreme coastal events? It's mostly storms and tropical storms, for example, and in particular two phenomena, the surge and the large waves that are created by the strong winds of the storms. And because of those storms are actually modulated by the global climate variability, the objective of this project is trying to understand the connection between the climate variability at the basin scale and the coastal vulnerability at the beach scale. In particular, we're trying to understand how climate modes modulate the storm activity and how the wave generated by those storms actually impacts the coastal population on the beach. So to do that, we use a lot of different models to try to understand this cascade of very complicated processes from the basin all the way down to the beach. But the main idea of this project is actually trying to reduce the complexity of these very complicated parameters and try to implement only the most relevant ones into simple conceptual models. So why do we do that? Because those simple models are easy to transform into forecasting tools. They're also really easy to set up because they basically can run on a laptop. And that's a strong advantage for emerging nations, for example, who usually don't have the computing capacity to run these really complicated climate models. And are also usually the most at risk. So a few results. We studied in the Pacific, and we realized that accounting for the dominant climate pattern in the Pacific, El Niño Southern Oscillation, in all its diversity and irregularity, was actually enough to explain most of the variants of coastal wave extreme all around the Pacific. And we can see that on this example in California, where we see that our model simulates the occurrence of climate extremes in red and their modulation much better than the previous state of the art. So what are we doing next? We're trying to think global and try to expand this theoretical framework and to account for new climate modes in other parts of the world, in other basins like the Northern Atlantic or the Southern Ocean, and to try to construct a global model of coastal variability. Also, one of the problems of coastal vulnerability is the access of data at a global scale. But now we are well into the era of Earth observation from space, and we have actually a lot of optical satellite data, and we are trying currently to compile the first global data set of shoreline variability all over the world. And by combining actually this global framework with this new data, understanding the connection between global climate and regional coastal vulnerability is actually more than ever within reach. And on that, I thank you all.
Thank you, Julian. Just like Christina was volunteered to do the opening this morning, Julian has been volunteered to do the conclusion tomorrow. So we'll be going through. Thank you very much, gentlemen, as we move on to the next panel. Thank you. Can I ask Professor Alessandra Gianni, thank you, and the rest of your team to join her? So Giancarlo Espinosa, come along, Louis Derry, and Katsumasa Tanaka. Yeah. I'll let you introduce your panel, yeah?
Yes.
And Alexei is available, is ready. So.
Good afternoon, everyone. I guess it's good to be volunteering as chair in the afternoon, so I have to stay awake. I usually have trouble with seminars at 2 p.m., but anyways. Yes, I think I correctly deduced that since I met Lou, Katsu, and Giancarlo this morning, that Alexei would be joining us online or is recorded.
He's ready. He's ready.
He's ready, Alexei? So the panel I won't introduce much because it's a very varied panel, as you will see. So we'll start with Alexei Fedorov, the AMOC, Atlantic Meridional Overturning Circulation and Climate Change.
Over to you, Alexei. Can you hear us?
Hello, everyone. I'm Alexei Fedorov. And I'm going to talk about the Atlantic Meridional Overturning Circulation, or in short, AMOC. Next, please.
We've lost sound from you, Alexei. You've turned your microphone off.
Okay, sorry. Okay, so I represent the project ARChange, numerical modeling of Arctic climate change, global ocean circulation, and basin interconnection. And this is our team, including collaborators in the United States. Next, please. So I probably don't need to spend much time introducing Atlantic Meridional Overturning Circulation, or the AMOC. There were previous talks, but in short, it's a complicated three-dimensional current system in the Atlantic, including the Gulf Stream and many other currents. And the thing about climate impacts of AMOC, well, the circulation transports heat from low to high latitudes, affecting sea surface temperatures, the atmosphere, and weather and climate patterns. Next, please. So one of the major concerns with global warming is the decline of AMOC. And this is a very robust result of many simulations with different climate models. The AMOC is declining, and there is evidence already that it might be declining already. However, the rate of the decline and whether the AMOC may even collapse in the future vary across different models and scenarios. And two major goals of our project is to investigate key factors that control the rate of AMOC decline in a warming climate. For example, Arctic sea ice loss can impact those rates. And second, quantifying climate impacts of AMOC decline. And today I want just to give you an example of our work focusing on the second question. How can we quantify climate impact of AMOC decline? Next, please. So we conducted simulations, numerical simulations with a state-of-the-art climate model. And we designed an approach when we have, for example, two simulations One with a decline of AMOC about 30% by the end of the century. This is just a regular simulation with a green light. And another simulation, this purple line, where we actually fix the strength of AMOC. We designed a specific procedure that allows us to fix AMOC while running in global warming simulation. Next, please. And so we can compare this purple experiment and green experiment and look how exactly, what are the differences when the AMOC stays the same or AMOC declines. And what we find first is that there is a relatively small impact on global mean temperature. If we fix AMOC at a steady value, then the global warming becomes maybe 0.3 of a degree stronger. And so there is a cooling effect of the decline of AMOC, but it's relatively small on a global scale. However, if we look at patterns of climate change, so the difference between these two experiments, and that's you can see on the right panel, there are large local regional changes of the local regional impacts of this decline. And in particular, there is a large region in the North Atlantic with colder temperatures. And what's important for weather patterns, this effect increases ocean-land temperature contrast, and that can lead to various things like a dry Mediterranean region, more storminess, and other shifts in weather and climate patterns. Next, please. And so in summary, we find that the rates of AMOC decline vary across the models, and there are many factors that affect those rates: Arctic sea ice loss, even tropical Indian Ocean warming, the extent of polar implications, and these are all the topics of the Arctic Change project. AMOC decline will disrupt temperature, precipitation, and wind pattern in the North Atlantic and other regions, including the drying of the Mediterranean, this North Atlantic Ocean warming hole, poleward shift of the jet stream. A good news is that predictions of like a movie of the days after tomorrow with a complete collapse of the climate system is not going to happen. However, this decline, AMOC decline, will disrupt temperature, precipitation, and wind patterns with many detrimental consequences to weather and climate. Thank you very much.
Thank you, Alexei. Next up is Giancarlo Espinosa, the hydrological cycle in the Andes-Amazon connection facing climate change and deforestation. Thank you.
Good afternoon, thank you very much. I am Giancarlo Espinosa. I am a Peruvian scientist working in Grenoble in France. So this is not my presentation. I can try, but it's not sure. So in this presentation, I will show you a general view about my project, Amanecer project, regarding the Amazon Andes connectivity facing climate change and Amazon deforestation. So this project is conducted in the IGEU and Institut de Géosciences de l'Environnement in Grenoble, France. The Amanecer project is focused on the Amazon River Basin, which is the world's largest tropical rainforest. This ecosystem of around 7 million of square kilometers is home of an extraordinary, unique, and irreplaceable biodiversity shaped by a coupled dynamics between the Andean Cordillera and the Amazon lowland. Over the Amazon basin, we found more than 2,000 species of fish, which is more than can be found in the entire Atlantic Ocean, and more than 10% of the known plant and animal species coexist there. The Amazon rainforest is also a buffer against climate change. It stores around 130 billion metric tons of carbon, which is equivalent of almost a decade of global emission of carbon. The Amazon River Basin is also one of the most critical elements of the Earth climate system. The Amazon River supplies around 20% of the total freshwater discharge to the global oceans, including sediment and transport and nutrients that come mostly from the Andean Cordillera. In addition, up to 30% of the Amazon precipitation is regionally recycled by means of the evapotranspiration of the tropical forests. This process sustains a high flow of moisture in the atmosphere known as aerial river. So this aerial river is a critical source of energy and water to the atmosphere and exerts an strong influence over the Andean hydroclimate and over the large-scale atmospheric circulation pattern. So the Amazon rainforest provides key conditions for the global energy and water balance and for the global climate equilibrium. However, due to climate change and deforestation, the Amazon rainforest is considered today as a biophysical system in transition. Indeed, around 17% of the total Amazon surface has been already deforested, and an additional 17% is degraded. Deforestation in Amazonia is expected to continue in the future, mainly over the central and southern part of the Amazon basin, as observed in this business-as-usual scenario. Regarding climate change, a more frequent and intense extreme drought has been observed in southern Amazonia since the beginning of the 70s, and the last 2 decades have been the warmest record since the last century. Due to these changes, and according to the scientific community, a tipping point of the Amazon rainforest is a real possibility, and the big question is how that may happen. Over this context, the main scientific questions of the Amanecer project are how global warming and regional modification of land cover could affect the regional and global water cycle, and also how will connectivity between the Andes and the Amazon be affected. The second question includes changes in sediment and nutrient fluxes from the Andes to the tropical Atlantic Ocean, and also this question includes changes in water resources for the Andean cities. Amanecer project is based on a methodology that includes observations and numerical modeling analysis. For instance, we use an atmospheric and land surface coupled model in order to provide future projection of the water cycle in the global tropics, and particularly over the Andean Cordillera. Indeed, in a recent publication, we have documented the deforestation impact on Amazon Andes hydroclimatic connectivity. For this, we analyzed the climate sensitivity to different land use scenarios over Amazonia, including a scenario where the Amazon is not deforested, which is the control scenario, and a scenario of deforestation in Amazonia according to this business-as-usual projection of the forest. Our result shows that the deforestation in Amazonia induced significant changes in the large-scale atmospheric circulation patterns, including a reduction of moisture that comes from the Atlantic Ocean to the continent. And as a consequence, deforestation also induced a reduction of precipitation, mainly in central and southern Amazonia, where deforestation is observed, but also we observe a reduction in precipitation remotely, mainly over tropical Andes, particularly over Peruvian and Bolivian Andes. So our results confirm that deforestation induced both local and regional impacts due to changes in the main state of the atmospheric circulation patterns, including precipitation over the Andean countries where water for millions of people depends on the Amazonian aerial rivers. Thank you very much for your attention.
Thank you, Giancarlo. Perfect timing, as you had promised. Next up is Lou Derry. CZ Top, the critical zone as a non-steady state biogeochemical reactor.
Okay, well, thank you. I'll talk a little bit about this project. CZ-TOPE is short for Critical Zone Isotope, and it's about water and water quality and how that is, how we're understanding how that can change in response to climate change. So, we all know that the amount of water we receive is changing as a response to climate change. We've seen that dramatically this year, both in Europe and the United States, as well as other places. But also what's in the water can change. And both of those parameters, the amount of water we get and what's in the water, are of direct public interest. But in fact, what's in the water is an important integrator of what goes on inside watersheds in a number of places. So here's a quick schematic illustration of a watershed. We have a number of things we have to think about. We have to think about how long the water resides in the watershed, what it reacts with will both control the water quality or composition. Both are changing with respect to changing climate. So we want to know something about the impacts of changing precipitation on these processes. And this is not only of interest for direct impacts of water quality, but the export of water from a watershed tells us a lot about what goes on with carbon cycling, with weathering and alkalinity fluxes, with biogeochemical fluxes, fluxes of nutrients and fluxes of pollutants. And so all of that is, all of those signals are contained in the water that leaves the watershed if we can understand them. One important parameter that we need to understand is that water in watersheds has an age, a measure of how long it's been since that water entered the watershed as precipitation and then exits the stream gauge. So that's also known as the transit time, and that's related to the many different paths that water can take in the system. So the water can take many paths, have different residence times or transit times within that system, and both of those different things, the flow paths influence what the water reacts with, and the transit times can influence how long the water has a chance to react with that substrate. So here's an example of a simulation that we're using to try and understand that. This is a simulation with a model constrained by age tracers, chlorofluorocarbon tracers, and it gives us an estimate of the mean age of groundwater and mean age of stream water in a river in Bretagne in France. And so we can see that this particular system has pretty old groundwater, but its age changes through the season. And the stream water is a mix of the old groundwater and younger surface runoff, which also changes through the season. So we get that age by injecting virtual particles, and when each particle comes out, we ask, how old are you? And after we integrate that over several million particles, we get an information on the mean age of the water, but also the age distribution, or how long is the tail on that age, which is quite important as well. We need to know the age, but we also need to know something about the chemistry and what the water is interacted with. Here's a small watershed with an event, just a flooding event. We use a rainfall event, which produces a flood as a sort of pulse input to the system. This is just over a couple of days, and we can see that the silica flux, in this case, increased by about an order of magnitude within half a day or so as a result of this rain event. Where does all this extra silica come from? Are we simply amping up the normal sources, or do we have new sources? And sometimes that's a difficult question to answer. So we're using some new tools, and one of them is the isotopes of different elements in the system. In this case, silicon isotopes. Silicon has both long-term geochemical interest and short-term ecological and biogeochemical interest. And you can see here that the silicon isotope ratio changes significantly during this same flood event, telling us that the sources and reaction mechanisms involved have changed substantially over the course of essentially less than a day in this system. So that's giving us a lot of information about the kinds of reaction networks. And we can include both the concentration of silicon and other elements and the isotope information critically in a reactive transport or biogeochemical reaction model that's coupled to the hydrologic model to actually understand the system and really be able to interpret what these variations mean in terms of processes internal to the watershed. So watersheds are complex, they integrate a lot of information, and the hydrochemical response of watersheds is a strongly coupled problem. It's not just hydrology, it's not just chemistry, it's not just biology, but it's all of these things and how they interact. This problem is a long-standing one, but it's complicated, which is why we're still working on it. But over the last few years, new developments in transit time modeling, new developments in biogeochemical reaction modeling, reactive transport modeling, high resolution, high frequency data systems that allow us to measure things at high frequency, and these new isotope system tracers are allowing us to answer these questions. And we can apply what I just illustrated for silicon to a lot of other systems. So this is the approach we're trying to take to get better predictive capability for the future, to be able to interpret these signals in a mechanistic way and understand what goes on inside the black box under the surface of a watershed. Thank you.
Thank you, Lou. Last one is Katsu Tanaka, overshooting the Paris Agreement temperature targets.
Yeah, thank you. I'm Katsu Tanaka from LSE France and the National Institute for Environmental Studies in Japan. So I'm going to talk about what the problems are if we overshoot the temperature target of the Paris Agreement. So the temperature target of the Paris Agreement is to hold the global warming well below 2 degrees relative to pre-industrial levels, and pursue efforts to further limit the warming to 1.5 degrees. So 1.2 degree warming here is where we are currently. Until today, many countries have announced various ambitious targets, such as net zero target by mid-centuries. Assuming that all these pledges will be fulfilled in reality, the global mean temperature is projected at 1.8 degree at the end of the century. On the other hand, if we consider only climate policies that are already in place, the warming can go as high as 2.7 degrees. So despite various announcements has been made by the government, there is still a possibility of overshooting the 2-degree target of the Paris Agreement. And these are some examples of overshoot scenarios, and these are generated by the integrated assessment model called ACC2. And now I raise two issues. So first one is the geophysical one. So unlike what's shown here, the temperature may not come back down to the 2 degrees because of various feedbacks in the Earth system that are not in this model. And one example would be the carbon side feedback. So the higher the warming is, the more CO2 may come from the soil due to the decomposition of organic matter. And there are some earlier talks today on permafrost. That's also part of this feedback. The another issue is on socioeconomic. We may not be able to bring the temperature back down to 2 degrees because of the limit of the CO2 mitigation potential. The potential of carbon capture and storage is not without a limit. It's inherently uncertain. So we also have to think about using other gases to reduce the temperature, especially methane. So now the question is how to balance the mitigation effort between CO2 and methane to sort of decrease the temperature under this pathway. So I'll introduce two studies to address each of these points. So first, this was done by a postdoc, Irina Melnikova, in a project. So she looked into the simulation results of state-of-the-art Earth system models, and then this is how the model responds to an overshoot scenario in which the atmospheric CO2 concentration peaks around 2050 and then decline thereafter. So there are two things here. The first, on the right, the blue curve, the ocean CO2 uptake actually peaks before the peak of CO2 concentration. So it actually responds to the rate of change rather than the concentration itself. The other finding is that both land and ocean CO2 uptake goes negative. So this means that the land and ocean can become a source of CO2 rather than the sink of CO2. So if we follow overshoot pathway, maybe more CO2 may need to be abated than anticipated. And this is the other studies. So on the right, I show that to what extent the mitigation of methane need to be strengthened compared to the mitigation for CO2 under each of these overshoot pathways. So essentially, the darker the green is, the higher the weight of methane is. And more technically, this was done by looking into the price ratio of methane and CO2, and I present the price ratio in terms of the global warming potential closest to the price ratio. But one of the highlights is that when you see this darker green, the temperature decreases. This means that the methane mitigation should be prioritized to decrease temperature if we follow the overshoot pathway in a cost-effective way. And in the Paris Agreement, they have actually decided to use GW100, and this is consistent in our results in up until mid-century. But from mid-century, it is more cost-effective to use a different type of index to compare between CO2 and methane to follow the pathway in a more cost-effective manner. So I discussed some issues related to overshoot scenario, And whether we can return from overshoot, I mean back down to the target level, depends on many things, but including also the fact that I discussed. So my short message would be that if we overshoot the temperature target, new issues and challenges may arise. So that's all. Thank you very much.
Thank you very much.
Thank you, everyone.
Stay there, gentlemen. Stay there because we're going to have questions and answers now. So, yeah. Before we go to question and answers, our cartoonist has been busy again, and let's see what Guillaume has to show us. Terrific. Okay, we've had a couple of questions online. If I can look them up here. Yeah.
Do you want to bring some more of the speakers to the podium?
No, we'll do it. They'll do it. So they can stay here. Whoops. Do you want to? No. You come and show it to me. I think go on. Who's got questions in the audience? Let's start there. Go ahead. Can I have a microphone down here? And who's it for?
This question for Julian. My question was, you were showing El Nino events with coastal vulnerability. Do you see that also for La Nina events, say this global seesaw, when you have East Pacific with El Nino, and then you have, say, Indonesia with...
Yes, there is actually a swing in the Pacific basin between El Nino and La Nina, and between the Western and the Eastern Pacific. So basically, when you have an El Nino event, you're going to have more waves on the western facade, like California all the way down to South America. Whereas when you're on a La Nina event, the wave activity is going to be increased on the other side, like in the Philippines, Japan, like these areas. And this picture is also complicated by the different kind of El Niños. So I'm not going to go into the much details, but you have also different kind of swings that happen between winter and summer. So you have a seasonal synchronization of these different ENSO events.
But would you say one is worse than the other?
Well, El Niño is worse for the West Pacific, for the East Pacific, and La Nina is worse for the West Pacific. So it depends on where you live, basically. So there's going to be more, actually both, more extreme events. So there's going to be more extreme El Niño and more extreme La Nina. So that's going to intensify this coastal vulnerability program across the Pacific. So I don't know where you live, but either if you're affected more by El Niño or La Nina.
Is Thomas Lavo here? Where is he? He was here. Okay, this is a question for you. It's come online from Ashley Badington, who we talked to earlier. The reduction in CO2 for Paris during COVID was much greater than the globe, which were only 5 to 10%. Why is this? How much of the energy consumed in Paris is from nuclear power?
Oh, God.
You have 10 seconds.
Thank you. Thank you, Ashley. Okay, so first thing first. Why is it so localized? A lot of the activities in Paris is about mobility, traffic. It's about a third of the emissions inside Paris. Direct emissions. I haven't made the details, but they're like indirect and direct. So direct, maybe a third of them are from traffic, which would be much higher in the US city, almost half. The energy production, so about a third comes from electricity production. It's a complex story because when you look at electricity, it depends what you're looking at. Heating in Paris comes from burning waste, trash. It's a big source of energy. So we have that huge point source in the middle of the city. On that, you have the electrical grid, which might be, and then the nuclear comes in the game. In the middle of winter, for example, nuclear energy is not enough. We also supply it with sometimes natural gas or even coal energy when needed. So it's quite a complex picture. I'm not going to go into a lot of details. Why Paris was so much of a reduction? Yeah, that's right. Because I think the heart of activities is mostly commercial. A lot of commerces were shut down, so mobility went down. Other places in the world have industrial activity. Some industries kept going. The food industry kept going, some service providers kept going. So it totally depends on where you are. At the global scale, it's also, you have to be very careful, the 5%, some countries didn't confine as strictly as what we saw in Paris. It was on different periods over the year. It didn't hit the same countries at the same time. So right now, I would say that the key point was for us to target a place where 90% of the activities comes from human-made fossil fuel emissions, not maintaining long-term activities and baseline functions of the state.
I think we got there. Good. We had another question also, which went to Alexei Fedorov, but since he was remote, he's replied. The question was, do you think your simulated impacts of AMOC would be different if you let the model simulation run to year 2300? I'm glad he answered that. Thanks for the question. It largely depends on the climate scenario used. If we fix the radioactive forcing at the level of the end of the 21st century, it will largely stay the same with perhaps a little stronger signal. However, if the warming continues, the AMOC will collapse completely with much stronger climate impacts. That was the answer I would have given. Who has a question in here? Behind you. Go ahead. Tell us your name again and who's it for?
It's Jim Clark again, Duke University and University of Grenoble. My question was also for Alexei. We heard in the plenary, one of the plenaries this morning, that we had multiple reasons to be worried about collapse of North Atlantic deepwater formation, especially when coupled with things like warming and melting of the Greenland ice sheet. And we got a very different sort of interpretation from Alexei Fedorov on that. I wondered if they're looking at different information or if they're looking at the same information and just interpreting it in different ways. Thanks.
That's for Alexei. He's not here, so we'll get his reply online and we'll get back to you. How's that? Another question? Yeah, sir.
Thank you, Ignacio Palomo from IRD Grenoble. I have a question to Giancarlo Espinosa. It was very interesting to see how deforestation is impacting not only biodiversity or climate change mitigation, but also precipitation and potentially water flows in the region. Do you foresee any applications on this in nature protection policies or environmental management in the Amazon and the Andes? Thank you.
I would try here. Be easier if you go here.
Stand up to the podium. Yeah, thank you. Yeah, actually we know today where the region more impacted by climate change and by deforestation, so where the hydrological cycle is more modified due to human intervention. So our next step is in this way perform maps and atlas for particular region where the risk of forest loss is more intense regarding biodiversity or human impacts. For instance, in the Amazon Andes transition zone, this is a region which is considered a hotspot of biodiversity. So this is probably a region very important to conserve. So yeah, this is a very interesting point that we need to we try to perform in the next step of project.
Great. Next question.
Thank you. So Philip Schuss from CNRS IPVF. I do have a question for Ridwan. So I've been fascinated by your AI approaches. I was wondering if the model has been developed for exactly this purpose, the Lawrence 96, which I believe gave it a history matching, or if this was taken from a different field, and if so, what are other applications?
Thank you for the question. Actually, the Lorentz 96 is a classical model actually already developed by Lorentz in 96, yeah, in the year 96. And what I did is that I took the 4 parameters that we can tune for this model. And those were the parameters I was trying to tune using the history matching technique. So that's what we did in the work did right now. So the next step was using history matching, but for example, the IPSL model, which is a very complex coupled model that has a lot of component, atmosphere, ocean, etc. So there were some works on atmosphere that have been done on atmosphere from another group. They showed that it works, that history matching works well for just the atmospheric components. Not much works on the oceanic components. So what I'm trying to do first is starting by the oceanic components, apply history matching there, and the challenge will be to apply it on the coupled model. That's really a midterm, let's say, goal. So I'm starting really step by step here. So that's what I'll do for the next steps. Thank you.
Anybody else? Yeah, go ahead. Here, why don't you come straight to the mic?
My question is for Rainer Kiko about export production, or how to, because your export from the euphotic zone seems to be high relative to standard models of export production, and your export in the deep zone seems to be low. So what do you think the relationship is between what you're able to measure and what those sort of kind of steady state simulations would imply?
So I think our observation values and the simulations coincide quite well. They are something between 3 gigatons of carbon per year and 10 gigatons of carbon per year. I think the problem that we have to consider is where does the carbon end up, and we still don't have a good depth horizon that we should look at. So I mean, this problem only came up to me last week somehow, that the balance is really so off. And so what I think, what we are measuring with the carbon flux is a flux of everything going down, which also includes very small particles which sink at very slow speed, something like 1 meter per day, which means also they need 10 meters to go down. And so I think much of what we consider at this depth horizon might not even make it 20 meters further down. And then it's still, to some extent, in the climate cycle, so to say, or in the active layer of the ocean, so it's a short cycle, so to say. So that's my thinking on this right now, but we have to look further into this, and that is actually what we can do with the data, because we have the size resolution. So we have, we know the size of all the particles exactly, and we can consider this in more detail. Yeah.
Alexi, I hope you're watching where you are. We have another question for you from Takeya. I was wondering about whether we're talking about an AMOC collapse or a regime change in the AMOC. Maybe you could answer here in the chat, Alexi. So, Alexi, there's a couple of questions for you there. Any more in the audience? Yeah, go ahead, sir.
Hi, Balaji here. A follow-up question for Rainer Kiko. Again, about the discrepancy. I think I'm following along the same lines that Luderi was asking. The number you showed, it flashed by very quickly, but it seemed alarmingly large. And I thought the discrepancy of where the carbon is going was getting smaller, because I'm an outsider, so this is I may be getting my facts wrong. But I thought that initially the land carbon sink had to be calibrated using the ocean carbon sink, and now you have independent estimates of the two. I thought the discrepancy was getting smaller, but maybe I'm wrong.
Yeah, I don't really know what to answer to that, actually. So I'm mostly considered about the ocean sink. And we've seen other numbers today that also say that the land sink is much larger. And so in total, we have a lot of uncertainties in this. And I would also like to stress that what we are measuring, or what we here provided is an estimate more or less over the last, although we use data from 20 years, we calibrated using data from the last 40 years. So it's to some extent a little bit weird. And what I think we can hopefully do in like 5 to 10 years is also that we really can generate a time series of flux in the ocean, that we really know how the global, how the ocean carbon sink actually changes over time. I mean, at least for the sedimenting flux, which I discussed, we don't know this. We really just know, or have a mean, and the mean, actually, the different estimates are between 3 and 10 gigatons, and that's a lot, actually. So much work to be done.
Thank you. Any other questions? Going. We'll have another session later on for questions. I want to thank the panel here. We'll come back at 5:10, so have a coffee break. But before we do, I see Guillaume's already busy on his next sketches. I think we should applaud him for what he's been doing already. So let's be back here at 5:10 punctual, and Christina will take over, and we'll be looking at the impacts of global change, and especially on biodiversity and ecosystems. And I understand there's a photo call. Where? Okay, there's going to be another photo call just outside before you have the coffee break. So, right now. Welcome back, everyone, to the final stage. And I have Christina here, who's going to take over and take charge. And over to you.
Thanks a lot, Chris. Thanks to the first session, we saw some pretty amazing projects that were contributing to our understanding of the processes, both past climate as well as current, and many of the problems that people are trying to tackle in modeling climate. So that was pretty incredible. So we've closed the first session, and now we're launching into the second session, where we're going to be looking at impacts of global change. This first session is going to be focused on a variety of ecosystems, and we have some pretty fantastic projects in the MOPCA program, and also some really beautiful slides. So I know it's late, but these will be really nice and sort of eye candy-like, so I hope it's pleasing for you all. Our session is made up of Jim Clark, Camille Parmesan, Nuria Taichiro, I had that, Carol Lee, and I will be finishing with the last talk. So I'm going to go ahead and turn it over to Jim, please.
Thank you very much. It's a delight to be here. If I could get the slides. I'm Jim Clark at the University of Grenoble with INRAE and also at Duke University. Our project is forecasting biodiversity change. Today I'm going to focus on the part on tree fecundity and forest change. Do I need to point this at something? I don't know what I did different there. A lot of us have been impressed with these massive forest diebacks we've been seeing globally over the last decade or so. Drought, forest insects, fires. What we have spent less time thinking about is what's going to follow them. That's going to depend on tree fecundity, and we basically know nothing about it. This picture on the left, the closest live seed in this picture, this is one of our sites in the Sierra Nevada, is 50 kilometers away. So clearly this is going to have a lot to do with 21st century forests. Beyond its contribution to the next generation of forests is how it impacts forest food webs. Climate change is not just affecting forests sort of at the landscape scale, but it's also continental in scale. If you think about the suitable habitat for a species like loblolly pine in the southeastern US, it's a real estate problem because, is this going to go backwards? Okay, interesting. Maybe that's why it doesn't work. There's bound to be plenty of suitable habitat in the future, but it's not going to be in the places where these species live now. And so somehow fecundity and dispersal is going to have to ensure that these species can get there. Our project is interested in what are these changes that are happening now and why. It involves global data collection by our own group and also modeling synthesis with the data collected by others. We call this effort MASTIF, which stands for Masting, Inference, and Forecasting. This is different from existing efforts in that it's not a meta-analysis. We're not doing statistics on published statistics. Instead, what we're doing is we're assimilating raw data from 12 million tree years, over 700 species, and we're doing it as one posterior distribution for the whole thing, all the raw data, because we're taking into account the full dependence between trees, within trees over time. We can do valid uncertainty. So let me just tell you about some of the initial results. I'll start with Darwin's abominable mystery. Why did angiosperms simply explode in the Cretaceous? There's an awful lot of hypotheses in the literature, and very few of them are really connected to fitness. Well, what we discovered is one thing is that angiosperms produce more seeds. So if you look at this sort of tree of life, the red colors are the low seed producers, and these are conifers. So we've got a very direct link to Darwin's abominable mystery. Ecological models assume that seeds just keep producing more seeds the bigger and the older they get. One of the things we found is that, in fact, trees get old just like all other organisms, and they actually start to decline. This has continental scale implications because the effects of climate change on tree fecundity come through an interaction with growth. The eastern part of the continent where we have smaller, faster growing trees are being stimulated in a way that the western part of the continent is not. We don't know anything about the biogeography of seed production. Where is there a lot of seed being produced? Well, we discovered there's a real hot spot in the southeastern warm, moist part of the country. This isn't at all where seed production is needed to facilitate responses to climate change. So we're finding out where the seed is and how it can contribute to species responses in the future. We wanted to extend this globally, and so we're interested in the fact that ecologists in the tropics are sort of preoccupied with these seed-consumer interactions. And so if you take a transect from dry taiga, this dashed line, to warm tropics, you see this threefold increase in productivity. And so most of the models have assumed that this is what fecundity must do. So in the lower left here, what I've done is I've just replotted this transect in terms of proportionate change. And so you can see this threefold increase from dry taiga to wet tropics. Well, that's what the models assume. There's no reason. This thing is flashing at me, so I think I better speed up. It probably started early or something. So it could go the other way. It could decrease, or it could actually increase beyond NPP. In fact, what we found is 100-fold stimulation in the wet tropics. And so this is sort of hyper-stimulating tropical food webs. So what we're trying to do now is understand how this affects food webs globally. This has brought in a whole range of collaborators on this project who've contributed to these interpretations and data. And we've got a number of papers that have come out of this. Thank you.
Great. Thanks a lot, Jim. And now we're going to hear from Camille Parmesan.
Thank you very much. Okay, my slide's not coming up yet. But anyway, I'm Camille Parmesan. My project, MOPCA project, is Climate Change Impacts on Wild Species, or KISS. But in the last 2 years, we've actually broadened it more generally to studies of the interconnectedness between humans, nature, and climate change. So I've been with IPCC for more than 20 years. And for the last 4 years, I've been coordinating lead author of the chapter on terrestrial ecosystems. And for the past 1 year, this has been a full-time job, which I could not have done without the MOPCA funding. So thank you very much, MOPCA. And as COLA, I've been able to ensure that not only are we assessing the impacts of climate change on nature, but we're also assessing the impacts that nature can have on solutions. And if we don't treat nature properly, the impacts it could have, creating a very strong positive feedback, making climate change even worse. And in discussions with governments, through official comments that they've been giving us and discussions with other disciplines within IPCC, it became very clear that the link between species and ecosystems was not very clear for most people outside of ecology. And so I made a point of including an assessment of the scientific evidence linking species to ecosystem functioning and services, and in particular, as we lose species, they become locally extinct or globally extinct, how that can make ecosystem functioning decline and make those ecosystems less resilient to climate change. Now, nature-based solutions were very high profile in the COP26 meetings, but I'd like to point out that the government negotiators in COP26 were handed our report in October. So even though it has not gone through government approval and publication, I like to think it's already had some impact. My own research is very diverse and very collaborative. We're publishing a paper on tundra moving up in the Andes, in the Peruvian Andes, faster than you'd expect from warming. It's actually following the glacial retreat. And the reason it's able to move to colonize so fast is this wonderful wild vicuña that makes latrines. Everyone goes in the same place, and these latrines form soil that allow the seeds to germinate in otherwise completely bare rock that the glaciers have left. In the Himalayas, we're seeing rhododendron moving upwards, as you'd expect, but fir trees are not. And we've done some experimental work to figure that out, why that's happening. As part of IPCC, we got spurred to do a global review of diseases of wildlife, and we were able to put together some very, very nice data showing diseases moving northward and upward, as you'd expect. We're trying to link that to whether that's increasing risk of these diseases in humans. It's extremely complicated, but we have found a few areas where we can do this. We're also just publishing a global meta-analysis on human-nature connectedness, and it's almost 60,000 people and more than 100 studies. And what we found is people really don't learn well in classrooms, that actually someone taking a yoga class in the forest teaches them more about the linkages between humans and nature than putting them in an ecology course. So now we're also devising some different experiments with education with young children to look for approaches that might be a blend of the two. Butterflies are my primary research organism. They're not only beautiful, they're fabulous climate change indicators. And what we've been able to show through 50 years of study on Edith's checker spot in the western USA is that climate stress is not just at the species range boundaries, which is where you expect. It's actually spread throughout the species ranges, and population extinctions occur being driven by extreme climate events. As the ground is getting hotter, we're seeing that it's going above the lethal temperature for eggs, which is about 48 degrees centigrade, and we're seeing a response to that. Eggs are lifting higher in this population, but there's a limit to how high they can go, because if they go too high, they get eaten by deer. As well as studying population extinctions, we're studying colonizations, and what we're finding is that the colonization process seems to release new genetic variation that was hidden. So what we're seeing in these newly founded populations are a diversity of traits emerging, which we're hoping will actually enable these new colonized populations to adapt to climate change in ways that we can't necessarily predict right now. Throughout all of this, outreach has been a very important part of my team's work, both films, writing popular articles. And I think this is incredibly important to get the science directly to policymakers and the public, particularly on how interconnected humans and nature are, to help create a more sustainable, climate-resilient world and go from being the biggest pest species on Earth to hopefully being the biggest healers on Earth. Thank you.
Great. Nuria. Great. Nuria, please.
Thank you. Yes, okay. My name is Nuria Teixido, and I am marine biologist, and I am based at the Laboratoire de Sonography de Villefranche and also the Stazione Zoologica in Antordon in Naples. I am marine biology, and I investigate how ocean warming and ocean acidification affects marine biodiversity, from single species to communities and ecosystems. And please, I would like, okay, yeah, thank you. Next slide, please. Oh yeah, sorry. And I am a field person, and I go to the sea. Please, can you play the video? Sorry. Yes, one moment. Yes, and okay, I am marine biologist, and I go to the sea, and if you like, you can come with me, and we will dive in one of the study sites in the Mediterranean Sea. This particular site is around 30 meters depth. It is full of life, extremely healthy, with many gorgonians, sponges, and many fishes. This is one of the most pristine sites in the Mediterranean Sea. And if I had to give you a headline, and if I have to sum up what I am doing, it will be this: observing a changing ocean. And for me, it has three major themes: observing in the meaning of understanding what is going on, understanding the patterns, and also acquiring data, environmental and ecological data. For example, here, I am deploying a pH sensor that continuously measures pH and temperatures of seawater. And here, we are conducting field ecological data, and we are assessing the health status of the reef. And the second and the third theme that I would like to point is the change that we see from year to year, over decades and centuries, and also the role that we play in that change. Sorry. The ocean covers more than 70% of the Earth's surface and is a critical component of the climate system. It absorbs more than 90% of the extra heat in the atmosphere, around 1/4 of the excess of carbon dioxide that we produce, and takes all the melting ice resulting from human activities. This process implies ocean warming and marine heat waves, loss of oxygen and change in the water circulation, ocean acidification, and sea level rise. These chemical and physical changes in the ocean have dramatic consequences for marine biodiversity and also for us. Marine heat waves are extreme climatic events and occurs when ocean temperatures are extremely warm for a certain period of time. They produce mass mortality of organisms, and they have dramatic impacts on marine biodiversity by pushing marine species and fisheries and ecosystems beyond the limits of their resilience, with cascading effects on our societies and economies. And for example, here we can see the same locality before and after a marine heat wave with loss of foundation species. These species, like gorgonians, corals, are the foundation, are like the big sequoias in terrestrial ecosystems. One of the first results, or the results relating with the marine heat wave project, we have been deploying temperature sensors in different sites and also over different depths, and we have found that the years 2015, 16, and 18 were the warmest, and we have related this with the percentage of damage of marine species. And for example, we can see in that coral, the red one, the orange one, the denuded skeleton. This occurs when marine species and corals, they are under stress, under heat stress. Thanks to a network of collaborators, we have been acquiring temperature data, and also we have been collecting observational data over the last 5 years across all the Mediterranean Sea. And we have seen that the eastern part of the Mediterranean is the hottest, and we have around 60% of all the surveyed rockers presented mortality, and this implies around 15 species from 1 to 40 meter depth. The Mediterranean Sea is a hotspot of biodiversity, but it's a hotspot of climate change. Marine heat waves are becoming common, are intensifying rapidly, and are extending over larger areas. And the critical outcomes of the 4 Oceans MOPGA project are critical data to improve our understanding of marine communities and biodiversity, powerful opportunities to connect community structure and function, and least but not least, we endeavor to contribute to nature ocean-based solutions while also contributing to protect marine biodiversity and nature. Thank you very much.
Thank you, Nuria. Carol, or?
Yep, great.
Great.
Thanks a lot.
We'll hear from Carol Lee.
Yes, thanks a lot for being here and for staying till the late afternoon. And do I have to advance this? Slides? Oh, wait. Oh, I see. Okay, great. Well, I'm glad to be here, and today I'm going to talk about evolution, specifically about rapid evolutionary responses to climate change. I'm a professor at University of Wisconsin and also working at the University of Montpellier in France. So why should we care about evolutionary responses to climate change? Well, first of all, climate change could have profound impacts on the biosphere. The biosphere is the sum of all interacting biological entities and is a key driver of nutrient cycles, including the carbon cycle. Now, with climate change, many components of the biosphere will have to either evolve and in some cases go extinct. Evolution will alter the rates of organismal metabolic processes and population demography, and extinctions will remove essential components of food webs, often with catastrophic effects. And as you can imagine, these types of changes will transform the feedbacks between the biosphere and the atmosphere and impact the process of climate change itself, usually in a very negative way. So, what are we interested in here? So the focus here is that on a global scale, habitat salinity is changing throughout the world. There was an earlier talk today about salinity change, and as you know, that at high latitudes with enormous volumes of ice melt and increase in precipitation, salinity, seawater salinity, is declining rapidly throughout the world. In a dramatic example, if you look at the Baltic Sea region, the Baltic Sea is a brackish water sea, but essentially it'll turn into a freshwater lake in the coming decades. This is a really dramatic change. So the question then is, in the face of climate change, to what extent could populations evolve to prevent extinctions? So my laboratory has been pursuing this question by performing population genomic sampling or sequencing whole genomes of hundreds of individuals of this beautiful copepod in multiple populations, 13 populations throughout the Baltic Sea and elsewhere. And as you should know, copepods are really important. They are the most abundant animal maybe on the planet, arguably, but definitely in the seas. And they form an essential component of food webs and provide one of the main food sources for fishes. So the question then is, can populations evolve through the mechanism of natural selection? That is the focus of the work in my lab. So to give you some basic background, if you have a population, at every gene across its genome, an individual inherits an allele from its mother and an allele from its father. So in a population, you have this genetic variation or allelic variation represented by these different colors. In the face of climate change, like environmental change, some alleles will be able to survive and reproduce, whereas many of the alleles that are maladapted will die and they'll be removed from the population. Then, hence, you get an allele frequency shift in the population. And that precisely is the definition of natural selection, and that is what we're measuring in our genomic data. So back to the question, can populations evolve, and to what extent could they evolve in order to prevent extinctions? And as I mentioned to you before, we're looking at populations of this copepod across the Baltic Seas and elsewhere, performing whole genome analyses of these populations, sequencing hundreds of individuals per population. And our novel results are that remarkably, across these multiple salinity gradients and across multiple laboratory and natural selection experiments, we see that with a change in salinity across only a few generations, this is only about 15 generations, we see a dramatic shift in allele frequency where the beneficial alleles rise rapidly in a population, repeatedly, the same alleles. So what we find is very specific alleles are necessary for adaptation to occur. And what was more surprising is that across the genome, if you look at different genes, specific alleles had to come together in individuals in combination for adaptation to happen. That is, there are epistetic interactions such that different interacting alleles across the genome at different genes needed to come together. And that was quite surprising. And in addition to that, in the original populations, these specific alleles had to be at relatively high frequency for natural selection to act. So in summary, the necessary alleles had to be present, the necessary combination of alleles at different genes had to come together in individuals for adaptation to occur, and these alleles had to be at relatively high frequency in the population for natural selection to act. So these are very stringent conditions. Many populations will not be able to meet these stringent conditions and are likely to go extinct. So knowing the genetic architecture or composition of populations would help us predict which populations will survive and which populations will go extinct. So the final message is that we need to understand the genetic structure of populations to predict and prevent future extinctions. And preserving genetic diversity within populations and preventing extinctions of populations is necessary to maintain this food web structure, to maintain its integrity, and to maintain healthy ecosystems. So with that, I'd like to acknowledge members of my lab in Wisconsin, members of my colleagues in lab at the University of Montpellier, and funding sources. Thank you very much.
Thanks a lot, Carol. So that collection of talks was quite a fabulous little Bio 101 collection for climate change. I'm really proud of this group because I think it's a pretty wonderful opportunity to see what biologists are doing in this realm, which we've discussed is kind of missing in some cases when people consider global change. So from my perspective, all of these talks and mine have to do with how organisms respond to environmental challenges. And I will tell you remind you that in Paris, I introduced this system that we thought would be a good candidate to explore these ideas. Shown here is the distribution of the Japanese knotweed. It's a globally distributed species now. It's providing a really unique opportunity to think about response to climate change and global change in general because it originally came from Japan, and from there it has been spread to Europe and the United States. And it is a classic example of this idea of the invasive species paradox, which I've listed up here, in that we think there's very little or even no genetic diversity in the invasive range. So essentially what we think is that this plant is a single clone that has invaded into Europe and also into the United States. And it's associated with this really remarkable change in traits. So here in China, in the native range, it looks like a typical understory plant, normal in the forest you see behaving like it should. But when it lands in Europe and the US, it becomes a monster and it tries to take over the world. So we're very interested in how is this even possible if there's no genetic diversity. As you just heard from Carol, we think that genetic diversity is really important for response to environment. Japanese knotweed seems to provide a paradox to that theoretical foundation that we always learn about in evolutionary biology. The other thing that's really remarkable about this plant, it's one of the most invasive plants in the world, contributing to this staggering number of $162 billion annually that's spent on recovering from the impacts of invasive species. So it also has a pretty important economic impact. So in Paris, I told you that we were planning to set up these transects. Since then, we have managed, despite the challenges of COVID and the fact that we couldn't actually go to China, we've managed to collect individuals from 50 populations in the United States, 50 populations in Europe, 50 populations in China, and 6 populations in Japan, for a total of about 800 individuals. and 2,000 kilometer transects in these three continents. For each of the plants, we collected trait information, genetic marker information, soil and climate data. And so far we found, in fact, the climates are very different. The native populations are shown here on the left. The Chinese populations are very different from the European and the North American populations. We also found that the number of stems we find in the plots is very different. So in China, you have very much fewer stems here, shown in this histogram for China on the left, and this blue and green histogram for the European and North American populations. So many more stems packed into a meter square. And one really fascinating result that we think might be contributing in particular to the success of this plant in invasive ranges is this pathogen presence. So here shown on the y-axis are the number of individuals that we measured, the percent of the individuals we measured, and more than 80% of the individuals we measured in China had evidence of pathogens, whereas in the invasive ranges, we had much lower percentage of infections. So the premise of our study in Paris was that we had this invasive plant that was a single clone living in all these different habitats. We could basically treat it as a replicated experiment to see how does a single individual respond to this huge range in climate. In fact, several laboratories around the world had documented that these plants in these pictures were the same genotype using classic molecular markers. However, we now have more sophisticated markers thanks to the MOPCA program that has funded our project. And now we think there's actually mutation going on in this system that might be important. So that will be one of the big aims of the coming year, is to identify how much diversity is really in this single clone that we thought was a single clone, and does it matter? Finally, I want to point out that many of these projects, maybe all, I wouldn't go so far, but maybe what we're trying to do here is not only describe the patterns of diversity across the landscape and how we can explain them based on climate or soil or other types of environmental factors, but what we really aim to do, and Carol mentioned this, is to be able to predict what's going to happen in the future to these species and what we can do to prevent extinction events, for example. And if we can take the information we find in our particular systems and translate that over into broader biological systems. And with that, I'm going to wrap up our session and turn it over to the impacts on human systems.
That's fine. You'll do that. Yeah. Thank you very much. That was great. If someone offers you Japanese knotweed for your garden, you just know to run away. Our final four guests. So this is going to be chaired by Laurie Hamlin. Laurie, you want to come on up with your team? Sylvia Schroeter, Maria Apergi. And then after this, final questions, and that'll be the end. Hello. So I'll leave it to you. Do you want to take over? You've got the slide there for your slides. Are you not?
I don't have it.
Okay, so I'll just let you introduce your team, your panel.
Okay. Can you hear me? Yes. So happy to be there for the very last session of today. My name is Laurie Hamlin, and what I'm going to do today is that, now, I'm just going to quickly go through what kind of presentation we will have, because I prepared, so I'll do it. And yeah, so this is the last session, but I think a quite nice way to finish today. So what we'll discuss is transition. Let it be to low carbon system or to energy transition, and have a particular look at regions that are the most at risk of social disruption due to climate change. So we first explore agriculture and land use changes with Sylvia Schroeter, PhD student at the University of Augsburg, presenting the results of the Monsoon project on the behalf of Prof. Jed Kaplan, that was with us in Paris, but couldn't be there today. Then we look at the resilience of health system, very relevant today, with Valerie Ride, that will be virtual. And yeah, it will present some results of the Climb HB project. So Valerie is a senior researcher at Centre Population et Développement, a research unit of Université de Paris, and Institut de Recherche pour le Développement. I don't know if they have English translation. I didn't have time to look, but that's what they put, so that's what I'm reading. Then we have Dr. Maria Apergi. Have your title here, Scientific Project Leader at the Institute of Advanced Sustainability Studies in Potsdam. And she presents on the behalf of Prof. Andreas Goltal, he was also with us in Paris, results of the ISI GET project on the development of an energy justice index for the energy transition in the Global South. Looking forward to hear. And finally, we'll examine some of the flip side of low carbon transitions with senior researcher Bruno Turnheim, leading the Ways Out project at the LYSIS lab of Université Paris-Est. So on this, I leave the floor to Sylvia, and then I let you just go as it's your turn.
Thank you. So yeah, I'm really happy to be here today and to talk about my recent research on my PhD on how smallholder farmers can increase their resilience towards climate change. And we've talked a lot about how climate change impacts basically everybody on this planet. We share this with everybody on this planet in common, but what we don't share with everybody is how strong climate change impacts us. So climate change is stronger in some areas of this planet, and not everybody has the same coping capacity to deal with these damaging effects. So especially farmers in rural areas of tropical developing countries are very vulnerable because they don't have a good way to deal with these damaging risks. And such an area is the northern region of Ghana, which is located in West Africa. And as you can see in the middle, they have only one rainy season. So this means the crop production, which is also the basis of the food security and the income and therefore the livelihood of the rural population, is based completely on this rainy season. And as you can imagine, if climate change leads to fewer but heavier rainfall events, this can lead to heavy floods and droughts, and leading to a crop loss, which can risk the security of these people and their survival, basically. So one way to mitigate these climate change impacts is to use surface and groundwater for irrigation. But of course, these irrigation systems, which add another whole cropping period in the dry season, these themselves are also impacted by climate change. So I went to northern Ghana to find out how resilient these irrigation systems are towards climate change, and if possible, how these can be improved. So one way to measure the resilience, or one indicator for resilience, is the crop diversity. And in my case, I choose crop diversity as a term, but here it means the number of different type of crops grown within one dry season. So if the farmer grows several different crops and not only one or two, he can increase the suppression to pests and diseases, and this can buffer and mitigate climate change impacts and increase the overall production. So what I found was that the farmers that I interviewed, so I did some group discussions, interviews with the farmers, and also some expert interviews. But the farmers found out that they mainly grow up to, or the majority of the farmers grow up to 5 different crops. But of course, as you can see, there's a big room for improvement here, or to increase the diversity, basically, because some farmers even grow up to 18 different crops in one dry season. So having this kind of baseline of the diversity of the crops now, I wanted to find out what causes this kind of crop choices, because in order to say, oh, this is how we want to increase the resilience, and we need to find out what actually impacts the crop diversity. So I asked the farmers, like, how do you decide which crops you're growing? And I came up with this range of factors, and then analyzed how each of these factors impact the crop diversity. So, for example, as you can see in red, if a farmer considers how much water a crop actually needs and how much workforce he needs, and if a crop has a high income, the farmers usually have a lower crop diversity in the dry season farming. But if they consider, if they want to be resilient to environmental conditions and adapt to the market demands, they usually had a higher crop diversity. When they considered the soil, their traditional farming systems, the diverse nutrition, and their diet preferences, and whatever they knew how to grow, this for now has kind of an even impact. So to have kind of confident but theoretical conclusions, which I'm happy to discuss with you, I found out if we would address these factors on a farm level, but some of them are on farm level and some of them are on policy maker level, for sharing the knowledge on locally grown crops, on improving the storage possibilities so the farmers can adapt to the market demands, by improving the water access and availability and supporting technology to reduce the workforce, supplying fertilizers not only for cash crops and regulating market prices and access. The farmers would have the ability to improve their crop diversity and the resilience toward climate change to have better chances to cope with extreme events. So yeah, thank you so much for your attention.
Now we're going to have Valerie. He's online.
So this is Valerie's been, I've made a recorded message.
Research project started with a simple observation: the link between climate change and the health status of population are the subject of much research around the world. However, two elements have not yet attracted enough attention from scientists. On the one hand, the healthcare systems are an essential determinant of population health. On the other hand, population mobility is a global phenomenon. It therefore seems essential to better understand, in a dual context of events induced by climate change and population mobility, how health systems were able to guarantee universal health coverage, one of the Sustainable Development Goals. This is at the heart of an interdisciplinary approach to health system research. But how can such a complex subject to be studied empirically, particularly in Haiti and Bangladesh, which are experiencing dramatic situations associated with climate change? In our experience, for an interdisciplinary approach to be fruitful, and for a team of more than 20 researchers from 6 countries to work together on original empirical data, it is often essential to have a conceptual framework. Since such a framework did not exist, we created it. So we patiently built it using a collective and participatory process and internationally evidence-based approach, which is always easier said than done. The strength of the CLIME HB integrative framework are the inclusion of the population as a component of the health system and in interaction with the health services, and the inclusion of resilience process and its outcomes. For the demand side, population immobility refers to all mobilities from daily movement to displacements or long-term migration, and all situations of immobility undergone or voluntary. The 3 symbols above refer to all events disrupting the determinant of population abilities, such as sudden shock, stress, and chronic tension. Determinant of population abilities include all socioeconomic characteristics of the individuals and their communities, from empowerment to various capital and health literacy. Population abilities to healthcare access encompass the 5 dimensions of access: the abilities to perceive, to seek, to reach, to pay, and to engage. For the supply side of the health systems, routines and perturbation involve all events disrupting or not the routines and habits of the supply side. They include sudden shock, stress, and chronic tension, which may originate from climate change and population immobilities or mobilities, among other events. Determinants of supply side capacities include all characteristics impacted by or resulting or not from the change following the events, such as the hardware or software of health systems. Healthcare accessibility encompasses the 5 dimensions: approachability, acceptability, availability, affordability, and appropriateness. Resilience, pictured in green, is the combination of the demand side and the supply side of healthcare access across exposure, sensitivity, and adaptive capacity. Depending on these 3 components, the healthcare system resilience can be characterized by accessing its outcome, healthcare access, which might collapse, recover, deteriorate, or improve. Health here, population health outcomes are considered the ultimate outcome of the health system resilience and an essential result of healthcare access. Now you know our secret. It's free access for open science. But building a conceptual framework is useless if it is not applied to the reality. If we do not confront it with the situation that people in Haiti and Bangladesh are experiencing daily and as a result of the induced climate change events. So, see you at the next Make Our Planet Great Again conference to present the finding of the empirical data we have just started collecting.
Hello, it's great to be here to talk about the EasyGate project. So EasyGate stands for Investigating the Systemic Impacts of the Global Energy Transition. And the main objective of this 4-year research project is to identify the potential risks that are involved in the process of the energy transition, especially for countries in the Global South, and then to identify solutions and ways we can address and minimize these risks. And in order to do that and meet our objective, we are working on a number of different work streams. And today I will present our work in one of these work streams, which is on energy justice, and more specifically on designing an energy justice index for the energy transition in the Global South. Okay, so as the energy transition accelerates, it raises several questions in regards to justice considerations. For example, who makes the decisions? What about future generations? What happens with more marginalized and vulnerable communities? And in general, how do we ensure that the costs and benefits of such a transition are equally distributed across different societal groups? And how we respond to these questions will very much define the type of transition we will have in the end. So we think this is a very important issue to study and investigate. So when it comes to the concept of energy justice in particular, it focuses on the societal and development implications of energy technologies, policies, and projects. And in the last year, there has been also a lot of attention amongst energy justice scholars on the energy justice implications of particularly the low carbon transition and renewable energy technologies. However, these tend to focus mostly, they tend to be qualitative and focus mostly on developed countries. And we strongly believe that more work needs to be done on also focusing on developing countries. And also we need more quantitative metrics, like for example, energy justice indicators that will help us also take a more quantitative approach on studying the matter. And for that, in order to fill this research gap, we are designing an energy justice index to measure the extent to which elements of energy justice are incorporated in the energy transition for different countries. We started by focusing on 4 case studies, which is Kenya, Jordan, Chile, and Malaysia. And yes, and we are designing the indicator for this 4 case studies currently. Oh, sorry. So the 3 core tenets framework of energy justice, which is the framework the majority of energy justice scholars focus on, includes procedural justice, which focuses on participation in decision making, distribution justice, which ensures that there is equal access to the benefits of energy systems, and recognition justice, which focuses mostly on making sure that the needs of marginalized communities are also represented. And we use these 3 tenets as the basis of our analysis, and then we use the 8-principle decision-making framework, which is also a popular framework of energy justice, to identify the indicator components that are associated with each of these tenets. So after we identified these components, we looked for measures and metrics in order to be able to quantify them. And we did this by looking at initial availability of secondary data, but then at a later stage we also conducted in-depth country fieldwork, not fieldwork, but data collection. And currently we have already completed the process of data collection, and we are in the stage of analyzing our results. So we believe that there is a number of important applications of this indicator, and we have summarized the most important here. And I'm happy to talk about them afterwards. Here I want to draw your attention in these spider graphs, where we basically are the results of a number of qualitative interviews we did with experts, energy experts from all our different case studies. And we asked them to rate how well they think their countries are doing in each of the individual energy justice components. And we wanted to do this in order to be able to corroborate the results of our indicator later. And this is an example. You can see, for example, Chile here is doing well in participation, and Malaysia is doing better in providing affordable energy to its people. And this is just an example to show you the type of analysis that can be done based on this indicator. And as I said, we are focusing on 4 country case studies, but we hope that this can be expanded in the future and it can turn into a rich data source that energy researchers can use. And that's it from my side. Thank you for your attention. Please get in touch with us or follow us on Twitter, and I'm looking forward to your questions. Thank you.
Last but not least, hopefully. My slides, please.
You do it.
I do it
You need to be patient
this
until
way.
it comes,
Okay.
something like that. Yeah.
Okay, wonderful. Or not. So I'm Bruno Turnheim. I'm a social scientist at the Interdisciplinary Lab on Science, Innovation and Society in Paris. I'm the PI of the Path of the Ways Out project, if this will work, of the Ways Out project, focused on the destabilization and phase out of socio-technical systems. So there are many ways to make an omelette. French omelette, Japanese omelette, rustic omelette. There are different styles, preferences, many recipes, and various degrees of executions, which might determine the texture, the shape, the failure of that omelette. Omelette making is an art, but with the right equipment and skills, you can learn to get better at it. There are many ways to achieve low carbon transitions. There are many possible trajectories involving different social, technological, institutional innovations. There are many styles of governance, decentralized, centralized, technocratic, participatory. Such choices, again, determine the shape, scale, speed, and feasibility of transitions. And we have little experience governing sustainability transitions, but we can get better at it. But this misses a central point, and that is you can hardly make an omelette without breaking eggs. Transitions involve making new things as well as breaking old things. If there's one take-home message, that will be it for me. The Ways Out project focuses on the flip side of transitions, the destabilization, decline, and phase out of existing socio-technical systems. It aims to better understand destabilization as a socio-technical process involving the breaking, removal, and transformation of established systems, to explore a variety of possible destabilization pathways, and to explore available governance options. And of course, this is more challenging than breaking a few eggs and cleaning up the mess behind, because the metaphorical eggs here are people, jobs, communities, economic assets, because poorly handled decline produces significant social and economic damage, leaving potentially entire communities behind, because some actors have vested interests in maintaining existing systems and significant resources to actively resist change, whilst others are particularly exposed to vulnerability and losses. There's little prior experience of phasing out established socio-technical systems, but the following historical cases from energy, mobility, and agri-food might illustrate some relevant dimensions. So the highly conflictual management of coal mining phase-out in the UK has produced significant and lasting damage in former coal communities. This was a rather rapid phase-out, but a conflictual and socially damaging one. In contrast, the German coal mining phase-out has been much slower, but perhaps more appeased. Tramways, once a major urban transport option, were actively dismantled to make space for the car. Trams were framed as noisy, outdated, dangerous. Trams disappeared very rapidly as well. Tram tracks were dismantled, essential lines were closed. And ironically, modern tramways were recently reintroduced in most French cities over recent decades. So phase-out can also be reversed. DDT, a powerful pesticide, was widely used in agriculture since 1945. Revelations of its disastrous ecological and health impacts led to opposition movements, leading to bans from the 70s and a worldwide ban in 2004. However, new procedures for the authorization of harmful substances also reinforced the concentration in the agrochemicals industry. This enabled the global rise of new pesticides productions and use. So here, an impressive substance ban reinforced the underlying systems. So, destabilization can be understood as a process challenging the stability of socio-technical systems, and this is how we understand it in our community. It involves, we posit, three core mechanisms. Firstly, the alignment of pressures threatening the normal functioning of systems. Secondly, strategic responses, notably by incumbent actors who initially deny and resist the need for change. And thirdly, the preservation or the transformation of prevailing regime rules or institutions. Empirically, it's possible to explore destabilization pathways based on these mechanisms in concrete cases. But in the real world, destabilization is also becoming an object of governance, deserving of political attention. Phase-out objectives are circulated and being discussed in political arenas. Policy options for deliberate destabilization include reduction objectives, regulations and bans, disinvestments, compensations, regional and industrial strategies, and so on. Deliberate destabilization also involves difficult political choices with winners and losers, as we've seen today. So while just transition remains an oxymoron, destabilization can be more or less painful, depending on how it is played out. And here my last slide. So COP26 has shown again how low carbon transitions can be obstructed actively with disappointing commitments for fossil fuel phase-outs. The inconvenient truth is that any transition requires the destabilization of established systems, and that this involves sweat and tears. Besides supporting low-carbon innovations, it is essential to develop active strategies to deliberately phase out carbon-intensive systems. We're making progress with understanding this. There are rapid and slow pathways, more just, less just pathways, orderly and chaotic destabilization pathways. And in our next steps, Ways Out aims to develop the strategic intelligence to be in a position to anticipate and accelerate system phase out. Thank you very much.
Not easy to finish off the last one of the day, but it was great. So we're coming up to the final bunch of questions from you, the audience, and online, and then we'll have a final view from Guillaume. So we have one question online. I didn't really understand it, but I think Carol did. It's basically, what do the commonalities code for? Are there no coding regions? Does that make sense to you?
Yes.
Okay.
So the question is, what were the alleles under selection during parallel evolution? So across multiple independent populations in the Baltic Sea and elsewhere, as well as in the laboratory selection experiments, which had 10 independent lines, often it was the same allele that was under selection, same set of alleles across the genome. And in many cases, it was the same actual SNP or mutation that was under selection, which was really shocking and surprising. And the largest category of biological functions that were under selection were ion transporter genes, genes involved in ion uptake from the environment, which makes sense because as the habitat salinity gets fresher and fresher, the organism needs to take up ions against a very steep concentration gradient from a very dilute environment since salinity is going down. So it makes sense that those were the largest targets of selection, repeatedly in independent lines in the lab and in the wild. Does that answer, whose question was it?
It came online.
Yeah.
Okay, great. Any questions, Zach? Yeah. Remind us your name and who it's for.
Hi, I'm Davide Ceratti from Institut Photovoltaique Île-de-France. I also have a question for you. I wanted to ask how strong is this evolutionary pressure with respect of other things, if you can make other examples, I don't know. And if I should expect a strong evolutionary pressure or a good response from more complex animals, or what is going better? More complex animals will respond better or worse to climate change?
Yeah, so that's an excellent question. How strong is the selection pressure? It's actually quite strong. If you compare temperature and salinity, it's predicted that the salinity change is going to be faster than temperature change, at least in the short run, because ice melt is dumping really quickly into the North Atlantic and Greenland. There's already a freshwater salinity anomaly. So in terms of selection pressure, it's very strong. The selection coefficient is actually pretty high. If you look at these habitats. Temperature is also having a dramatic effect, but the effect of temperature is a little bit different in that salinity, the target for salinity selection is actually smaller. Temperature affects all metabolic processes. It has a very global effect on the animals, so it's affecting many, many more genes. But I think salinity change on average is happening more quickly in many of these habitats. I don't know if that answers your question. Yeah, especially in high latitudes. And then what was the second question about complex organisms? This is affecting everything. It doesn't matter if it's complex or not. For example, if you look at temperature or salinity, they're going to affect everything from bacteria all the way up to mammals. So the complexity is not an issue. These are physiological responses. So all organisms from bacteria to protists to algae to plants to animals all have a response to salinity change. Salinity structures all of these organisms biogeographically. So the complexity is, do you mean more generation time? Generation time would have an effect. Sorry? I think complexity is not so much the issue as generation time. If an organism has a long generation time relative to the rate of change, it's going to be harder to respond to selection because the unit of natural selection is generation time. Every generation, the allele frequency can change. So if generation time is long, like a whale, if generation time is 100 years, it's going to be really difficult to respond to selection. But if generation time is 2 hours, like a bacteria cell, then it can respond very quickly to environmental change through the mechanism of natural selection. Does that answer your question? Okay.
Yeah.
Okay, it's a double question. So I have one from Sylvia, and usually when people talk about resilience to climate in agriculture, in at least developed countries, a lot of money is spent on new species, resilient species, right? Grass being changed for drought-resistant grass, etc. What's going on in Ghana? I was wondering if it's all about just diversity in species, or is it also about getting new species to resist to climate change? And my double question was after for Bruno, and then I'll let you talk. What about people's opinion in your governance model? So do you also take into account the fact that in democracies, maybe people don't want, so it's beyond the will of governments, they more respond to the people. So to flip it, like, it's not only about the government deciding, it's about people willing to do something about it. So I was wondering how you take that into account.
Speak at the podium is probably easier.
But I think it's off. Can you turn it on? Okay, thank you. So for now, there's not that much focus on the kind of like what's going on farm level that much, but the government highly supports rice production because there's a high demand in the cities for it, and at the moment it's imported a lot from Asian countries, and they want to support the local rice production. So they do have different varieties of rice to kind of also adapt to climatic changes, but that kind of leads to monoculture rice production in the dry season, which is to be discussed if that's the ideal solution. So yeah, that's why I wanted to find out, like, can you also improve the resilience with crop diversity? But yeah, at the moment, the government subsidizes the monoculture rice production a lot. Did that answer your question? Okay.
Yeah, thanks a lot for that question. Socio-technical systems are social and technological. So they're made of material elements, social elements, people interacting in networks in their various functions, but also institutions, codes, cognitive institutions, rules, formal and informal. The way we formalize, and don't forget, we're not positivists in our field. The way we formalized destabilization as a combination of pressures, responses, and changing commitments also applies to these people. So in terms of pressures, we see pressures from civil society, we see pressures from all sorts of groups asking, so destabilization pressures emanating from society, as well as from other aspects of socio-technical systems. In terms of response strategies, denial, we also see this at the level of communities, individual social groups, etc. And again, changing commitments to prevailing structures and regime rules, this can also be applied at this level of people and communities.
Thank you. Any more questions?
Hi, this question is for Christina. Are there any economic benefits for the knotweed? So if you can extract fiber and like hemp, or medicinal properties like cannabis or something? I don't know.
Yeah, thanks for that, Henry. There are a couple of answers to that. So I think Chris mentioned, somebody mentioned, oh, it was Stefan who mentioned that knotweed is known for the resveratrol in the roots. So that's something that people really like. It's actually harvested in the native range for traditional medicine. So this is one of the sort of pet ideas that we have, that's why it's not such a menace there, that the people actually harvest it so it can't get too aggressive. So it does have that aspect, sort of some medicinal aspect that we don't really embrace in Western cultures, but they do in Eastern. And as far as your other question about does it have other benefits, there are farms of Japanese knotweed in Germany currently growing it for biofuel. And you can imagine this, if you've seen it, it gets massive, it grows really densely, so it does have those potential properties of providing tons of biomass as a biofuel. So far, it hasn't really turned into anything phenomenal, so we'll see if that becomes something. And then I think in terms of actually harvesting it in the wild, where it's a problem, then you have all of these difficulties of it's on private property, it's not grown in a way that needs to be grown to be harvested, and it has all of those other cascading problems associated with it. But it does have some of these properties because of its fast growth and ability to just go wild. Thanks.
Thanks, Christine. Go ahead.
Jérôme Chave. I have a question for Camille, actually. One of your results that you presented is that children don't learn at school about nature's interactions with humans, which is, I don't know if that extends. As a parent, I was really appalled by this, and I would like to hear from you, how do we go around this problem? Is there some concrete ways as, I don't know, as parents, as teachers, to improve the system, basically?
What a great question. So first, the big meta-analysis was almost all adults. So this is adults who are taking environmental science courses in college or ecology courses versus adults doing yoga and meditation, that kind of thing. And half of it was experimental, so pre and post testing, which is really why it surprised me so much. But what we are doing with the education is working with little kids between 5 and 10 years old, thinking that maybe that's the age to really be trying to teach them basic ecology, essentially. But what we're doing with our experimental approaches is we're doing it in multiple different ways to try to figure out how much interaction do they need to have with nature as you're training them with the information in order to have it really connect. So we're doing classes completely out in nature, we're doing some sort of half and half, a little bit of lecture, then you take them out and you show them things, and some just visually, just showing them videos like the wonderful video that Nuria had. Is that enough? Or, because in the cities, in urban areas, you're not going to be able to take every kid out into nature and teach them ecology. So we've only just started this, but I'd say actually teaching them the same ecology as you would in the classroom, but doing it outside and sort of pointing out, okay, there's the tree. See, the forest is cooler and wetter. You go into the meadow, you feel drier and hotter. That seems to really work very, very well, but it's early days.
Any other questions? Okay. Before we finish, let's just see what Guillaume has had to say about this afternoon's session. If we can just have a look on the screen. Pretty good. It's been a very long day. I want to say thank you to everyone, obviously, for your presentations. Fantastic. We worked on them a lot. Superb. Hey? You would know. Oh. Thank you. I want to thank the technical teams. They had a bit of a issue in the morning, and they resolved it and sorted it out. I put wires here and there. I don't know how they did it, but they did it, and it worked. So I'm sure we're all begging for more tomorrow. The good news is we can have a lie-in tomorrow at 9:15. So great that you're all here. See you all again tomorrow. Good evening. Thank you.